Hi, everyone. We're very happy to see you joining us live at Vilnius Machine Learning Workshop. Very much pleased to see you all here. Now you should be able to see my first title slide, which is a title slide of our event, as well as the co-organizers with whom we kind of arranged the event, and we're working on all of the details of the event. So it is myself, Jeff, but also Dovydas, Linas, Viorika, and Razvan, from whom we will hear a few words now, starting with Dovydas.
Hey everybody, my name is Dovydas. So happy to be here today. So excited to meet all of you. We worked pretty hard to make this Vilnius Machine Learning workshop happen, and I'm so happy that we made it. So just a few welcoming words. I hope that today will bring you some important insights, some amazing talks, and give you an ability to ask questions to really world-class speakers. I'm giving my mic to Linas now.
So hello everyone. First of all, obviously it's a pleasure to meet all of you, including the speakers, participants, and it's really good to say thanks for the organizing committee as well. So I really think that we will have the intensive 2 days, and we will have interesting talks, and let's take the most out of it. And as far as our ecosystem goes, I truly believe that this event will strengthen our local Lithuanian community, and this is one of the main goals of this event. So, good event.
Thank you. I'm super happy to be here, and I wanted to take this opportunity to say a few words about the EML community that is co-organizing this event, and just to say sort of what we stand for and what our goals are. So the EML community was started by myself, Viorika, and Doina, and we're all from Eastern Europe, more specifically from Romania, even though now we're researchers, so in my case and Viorika's case in the UK, and for Doina in Canada. And but however, through the interactions that we had with the local communities in Romania, but not only, in general in Eastern Europe, we've noticed that there's so much potential and so much really good research happening, which more often than not doesn't really surface at sort of the main machine learning conferences or workshops. In general, we've seen the Eastern European community to be underrepresented in these places. So our goal through EML was to strengthen the Eastern European AI community. So we want to promote and encourage the research happening here. And we firmly believe in equality and diversity, and we strive to improve sort of the access of education to everyone interested in machine learning. So this is focusing on Eastern Europe, but not only. And we believe strongly in networking and in connecting people. So at our events, they tend to be open to everyone, and we strive to have strong representations from everywhere. And I'll let Viorika say a few more words about what we've done so far.
Okay, thank you. Hello, everyone. Very pleased to be here. I'm actually sad that we're not actually in Vilnius, because I would love to visit. But yeah, hopefully one day we'll be there in person. So yeah, just to say a few words about what we've been doing so far in our EML community. So we started in 2018 when we had our first summer school under the name Transylvanian Machine Learning Summer School. And that was organized in person in Cluj-Napoca in Romania. Then in 2019, we moved to Bucharest, still in Romania, just because it was our start. We were just starting organizing these events, and we were more familiar with the Romanian ecosystem. Myself, Razvan, and Doina being Romanians. And then, of course, the pandemic happened in 2020, so we had to move the events online. But virtually, we were in Krakow in 2020, and then in 2021, we were in Budapest. So just two weeks ago, we were in Budapest. So in parallel with organizing the summer schools, we also organize smaller events like workshops to get to know different local communities. So we had such a workshop in Romania, in Timișoara, and then we also were in Ukraine in 2020, just before the pandemic started. Yeah, as Razvan mentioned, we really strive to facilitate access to education in machine learning. And for the in-person events, at least, you probably know that there are quite a few machine learning summer schools organized in the West. But the cost of these events are generally very high, like to register and to attend. The costs are very often not affordable for students in Eastern Europe. So we are really trying to change that by bringing in sponsors. So as you've seen here as well, we rely on sponsoring companies, and we do that heavily for the summer school as well. So because we offer very low registration fees due to sponsorships, we then have a very strict selection process. So yeah, maybe for the in-person events, you might have heard possibly that it's quite hard to be accepted at the school. But we believe that this is the right way to do this, like to have very low fees so that everyone that is accessible to everyone. And then we put we put emphasis on the talent of the people, and we want the people that are motivated and really interested in attending these events. And this is also a healthy way to organize such events, also because we bring together industry and academia. So in this way, students can actually see that there is a lot of interest from the industry. They can actually see the careers that they could follow by getting into the field of machine learning. So yeah, I think this is a good combination, and I'm really excited that we will have this workshop here, so you get a feel of how these events are organized. And yeah, maybe this will inspire you to apply for the next year's summer school that we haven't announced yet the location, but keep an eye on our webpage. Thank you.
Excellent. Thank you, everyone, for the introductory talks. Now I'll briefly go over some of the housekeeping rules for the event. So all of you are hopefully watching this stream from vmlw.live. This is where you will see the stream itself. You can also find it on YouTube. But the web page itself is useful because you will be able to ask Slido questions and participate in the polls, participate in the quiz that we're going to run in between the talks. Also, please do log in onto Slack, and we very much encourage you to introduce yourself and start communicating through Slack with one another, kind of building up that community and networking with one another. So please do that. So we will be using Slack, Slido, and Twitter mainly for communication. So please do look out to these means of communication. Now, briefly, some stats about the event. We had more than 600 registrations to this event, and they were all from all kinds of industry and academia. We had PhD students, we had faculty members, and we had also people from the industry. So we are very excited to see you all here. As a warm-up, we would like to see how many people are actually here. So let's just run a quick Slido poll. You should be able to see it on the event live page. So you should see the question, which country are you based in? And you will be able to enter a word. So we're just gonna run it for a few minutes. Please do enter your answers there. This is kind of to get warmed up how we're going to use the tool throughout the event in the next 2 days. So please do use it, and we kind of practice using it. We see that answers are coming through. Exciting, close to 100 answers already just in a few seconds, so very exciting. All right, answers keep coming through. Excellent, excellent. Now, because of time, we'll probably have to move to the next slide question as well. The answer is still coming through at quite a fast pace. We're above 100 already. All right, so let's go to the next question now. And next question is, what is your occupation? We also would like to see what kind of occupation, what kind of background people are watching this stream, kind of to compare it with the people who have registered. See the answers are coming through as well, and we will share these answers later on as well. At this point, we will proceed with the schedule. So some more statistics while you fill in the answers. We had 35% female, 61% male, 0.5% non-binary who registered at the event, and we're very much excited and we very much welcome everyone at the event, and we do encourage diversity. So please tell your friends, please tell your family members who might be interested in machine learning to participate in these events. We very much encourage that. And we are very much excited to see you all here. So please do share throughout the event, through LinkedIn or Twitter or Facebook with your friends, what is going on at the event, maybe what you have learned. We very much look forward to this, and please do tag either EAML community on Twitter or Lithuanian AI on Twitter, so then we will retweet and kind of try to amplify the message that we're trying to spread here. We very much thank you, all of the awesome speakers who agreed to participate in this 2 days workshop. So huge thanks to all of them. Hopefully you're excited about the speakers lineup as well. And you will see half of them today. We also very much thank the partners who are kind of partnering up with us to share the message about the event, about it happening here in Vilnius in Lithuania, specifically universities and also Women Go Tech. We very much encourage that, and we'll hopefully amplify these messages through this event as well. We also give huge thanks to the sponsors like Vinted, Scorify, and Biomatter Design and Nascent, who provided resources to kind of make this event happen, and make the stream happen, and make the Slido happen, as well as the other general logistics. So huge thanks. Regarding the schedule, all of you have seen the schedule hopefully already. Here is just a reiteration of the schedule. Specifically, there are details about today and tomorrow. Tomorrow morning during the welcome message, we'll announce the tree planting initiative by Vinted. We'll also mention the EAML lottery winners who will earn book hard copies, and also EAML project winners tomorrow night, which will be announced by Viorica and Razvan. So just stay along for that. It will be exciting. Also, Vinted will be awarding the lottery winners and quiz winners with free books. So you'll be able to get free excellent books about machine learning and causal inference. And these will, the quiz parts will happen during breaks today. It will be free questions during the breaks. And the winners of these questions, the free winners, will get the free books to choose from. So very exciting. We try to encourage education as much as we can. And that's all as far as the schedule and general guidelines. There were a few questions in the Q&A if the stream will be available later. Yes, it will be available. So you can just click through the VML live onto the YouTube, and you will see that it is on YouTube, and it will be available later on as well. So without further ado, we will go to our next speaker, Razvan, and yeah, Razvan, passing it to you.
Thank you. Jeff, maybe you can, if you could stop sharing. So, okay, perfect, thank you. Okay, perfect. Okay, thank you so much. So yeah, today I wanted to talk about a topic that I've spent quite a bit of time working on, namely continual learning. And I just sort of want to phrase why this is an interesting problem, and yeah, what can it do for typical machine learning in general. And just a few words about myself. So I'm currently a research scientist at DeepMind. Before that, I did my PhD in Montreal, working with Professor Yoshua Benjo. And as I mentioned before, I'm sort of originally from Romania, where yeah, cool. So let's sort of jump into the talk directly. So I wanted to start with a little bit of motivation for continual learning, and I guess sort of the tagline that people usually use when they approach this problem is sort of this idea that the world is non-stationary. So briefly, what that means is that whenever we do machine learning, we tend to work with a fixed data set where everything is static. We train that system, we evaluate that system for that particular data set. But then when we deploy the system, we need to interact with the world, and the world keeps changing, right? So the distributions that the system will need to face while interacting, while being deployed, will change over time. And there are many examples. You can go from language, where like new words keep emerging all the time. So for example, in 2020 we had the word COVID that became extremely popular in the news and everything, and language models that were trained prior to that would basically don't have this word in their vocabulary. Or things like robotics, where you have tear and wear, where even the robot itself, the way it reacts to the commands that you give to it changes over time, or things like health, right? And just to reiterate what I said, sort of deep learning works really well, but what it really does, it's sort of just a very powerful tool that can work with big data sets. So it expects everything to be fixed, and it relies on lots of different ways to kind of be able to work at the scale and parallelization and so forth. But fundamentally, it relies on gradient-based optimization, which requires an IID assumption. So the way optimization works in general, it requires this IID assumption. So it requires everything to be static, and for you to be able to sample IID from it. And this is sort of different from how the world works, and maybe even from how we as humans work, right? So actually, humans are really bad at learning in an IID setting. So sort of imagine you need to learn for your exams, and then you have to like randomly sample from different topics, right? You read a sentence from the math book, and then you jump to geography or biology, and that's just impossible. And if we are like a big goal in machine learning, many times tends to be sort of our desire to imitate or to get closer to sort of human intelligence. And Thurman Griffiths has some really interesting work on this topic, and some interesting thoughts on it. So in this particular paper, Understanding Human Intelligence Through Human Limitation, he argues that actually sort of the way our intelligence behaves and exists depends on the limitation it has. And sort of this kind of just, again, highlights the fact that what we're doing now with machine learning, it doesn't seem to go in the same direction with how like human intelligence behaves, just because it has very different constraints and very different protocols and paradigms in which it works, right? So the fact that humans learn in a continuous way from highly correlated data is somehow affects sort of the kind of solutions we find, and it potentially is impossible for an ML system to reach the similar solutions without working in the same setup. So the way, as a research problem, the way this is being formulated is through the continual learning or other, again, as many times in the research community, you have sort of many subfields that are very heavily related. So I guess continual learning, lifelong learning, they're extremely similar. So you can use either term, whichever one you like. But in general, this definition is a very pragmatic one, and it's usually done by defining a protocol, right? So when we want to define continual learning so that we can try to study systems that learn in this setting, we talk about sort of the setup. We say, okay, we will have a sequence of tasks. You'd have to go over them one after the other. You have to keep learning, and then we have different variants of how this sequence of tasks might happen. We might have smooth task transitions where you kind of blend from one task to another, where you can have very sharp transitions where, up to point T, you do task 1, then you suddenly do task 2. You might have repetitions of tasks. You might have that every task is unique. The task might have different types. We could talk about unsupervised, supervised, semi-supervised, RL, whatever you want, but like different kinds of objective, different kinds of outputs, right? They might not live in the same space. You might not even have tasks at all, right? It might just be a continuous stream of data that changes somehow in an interesting way. So that's sort of the first half of what you need to do when you start defining continual learning. So you have to define the protocol and what is that you have to deal with. And the second part is, what do you want from a system that is able to solve this? And Usually this comes as a list of desiderata. So, people would say, okay, I'm training the systems, and what I want to do is I want to have a system that once it learns task 1 and it goes to learn task 2 and 3, it still remembers the solution of task 1. So this is usually, not suffer from catastrophic forgetting. A second desiderata that we typically ask for is that we want the systems to learn faster and faster, right? So we want the system to show forward transfer because, task K and task 1 might have something in common, so you want to exploit that. So when I hit task K, I want to start learning faster because I have this prior knowledge that I've acquired at some point in the past. And so this will be forward transfer, or you want to have backwards transfer, which goes sort of the other way around, which says, okay, if task K and task 1 have something in common, and now I'm learning task K, I somehow want to improve on task 1 as well, because I'm learning some skills that would be useful for task 1. So if you put me back in task 1, I want my performance to increase. There is this concept of plasticity, which means that the system can keep learning. And there's also restriction on model size. And this is particularly when you're thinking about a lifelong learning scenario where you're going to have hundreds of tasks that you have to go through. If the amount of compute that you need to do inference or even to do learning increases with the tasks and increases in a bad way, like, I don't know, quadratic or exponential or whatnot, then this will become very quickly prohibitive to you. So what you really want is a system that doesn't need to pay an additional cost, a computational cost or memory cost or model size cost. I think there are different axes and different people care about different care about combinations of this, but ideally you want the model to a certain extent to stay constant, or at least the computation to stay constant. And I wanted to add a note on the plasticity, so in this ability to learn, because it's sometimes kind of a bit tricky, and I just sort of want to clarify what I mean by that. So there are potentially 3 things that people can think of when they think about plasticity or the ability of the system to keep learning. So the most traditional thing that people have studied in the past is sort of this idea of forward transfer. And in forward transfer, what we really mean is that we want that if task 1 and task 2 are related, we want that when we learn task 2 to start learning faster. So it's all about speed of convergence, right? So the assumption is you will be able to learn task 2. That's not a problem. The only question is, are you going to learn it faster, or are you going to learn it as slow as if you haven't seen task 1? And this is sort of what people usually cover under forward transfer. Another potential problem that comes into play that was described in Chaudhary et al. It's called intransigence, and this is the idea that you're unable to optimize. So what might happen is, because you've learned task 1, you're now at a particular initialization that makes it impossible for HGD to learn anymore. And you kind of get stuck. So you can't get training error or test error go down. And I think this is sort of a very interesting question as well for optimization perspective. But the last thing, and this is sort of slightly new, and I think something people haven't paid attention that much, is this idea that you might be actually losing the ability to generalize. And for those who are kind of interested in kind of quirky ML problems, I would suggest for you to look at this paper from Jordan Ash and Ryan Adams, where what they show is that if you train on half of CFAR and then you fine tune on the full CFAR, you can't generalize as well. So basically, you can't get the same generalization. There's a generalization gap that appears. In both cases, you get your training error to be 0, but you can't get the same generalization. So it seems that somehow pre-training affects your ability to generalize in a way that we don't want. And this can be very problematic in a continual learning setting where, as you go from task to another, if you lose this ability to generalize, you basically lose the ability to learn meaningful solutions to future tasks, even though you can reduce the training error that you see for any future task to 0. Okay. And I guess the main point and the main issue why continual learning is so hard is because the way it's defined is through this list of desiderata, and they tend to be contradicting each other. So once you start playing in this space and you start trying benchmarks and you start trying methods, what you realize is that what we actually after is some kind of trade-offs. We know we cannot maximize all of these different things at the same time, and we need to pay something to get something. And the question becomes, what is this optimal trade-off that we're after? And this is sort of a really hard problem, and it's a hard problem because most likely there is no one trade-off that we actually care. So depending on the setting that you're in and depending on what you're trying to do, different trade-offs make sense. This kind of emphasizes the need of having like some real-world problems that we might want to tackle right now, because it seems that the data itself like imposes a trade-off that makes sense. And I think this has been a continuous issue in the field, is the fact that we've been working a lot with benchmarks and with algorithms that are developed for these benchmarks, and we're kind of solving and we're finding certain trade-offs that might not be meaningful in the end, and that's sort of just a continuous tension in the field. And it kind of boils down to the question of like, okay, what do we want to use this continual learning system for? So I gave you initially like a grand scheme motivation, and about human intelligence and how humans learn, and the world is non-stationary and so forth. But then like we can't really go directly for that problem, because there's no way for us to test our systems in that kind of settings. So the question is, tomorrow, if I want to use a continual learning system, what is that pragmatic problem that I might want to go for? Or what is the reason I'm trying to do sort of the research in this space? Okay, sorry, just going to the next slide. And I've tried to list sort of the reasons that you or anyone else might come for trying to deal with this problem. And there are many reasons that make sense, and there are many settings that you'd want to use this. But like for me, I do like sort of this angle that the data is really important, and I do like sort of the idea of us coming up with the real benchmark that we care about. But for me, it's also like, and I want to kind of highlight this, that there are other ways to solve this contradiction between the different ones of CL, and that's kind of just changing your perspective of why you're doing CL. And I've highlighted this particular one point that I'm particularly interested in right now, which is, for me, CL, it's the study about how we can accumulate knowledge in a way that's reusable in the future. So for me, CL is sort of this idea of us building on the knowledge that we have and being able to learn and use it to learn more efficiently after that. And what we can do is, we can, even in toy domains, we can check whether the mechanisms that we have allow us to do any of that. And to kind of go a little bit more in detail of what I'm thinking, I want to present. So some of you might have already seen this, but I like thinking a little bit about sort of what the ID assumption for gradient descent is, and how sort of this plays into continual learning and in sort of this theme that I'm trying to build here. So gradient descent, gradient-based optimization is something everyone probably knows. It's a very fundamental algorithm that's been with us for more than 4 decades now, and it's what everyone uses. But it always makes sense to go back to the basics and try to sort of reason through how these algorithms works and what they do. And one way of thinking of what gradient descent does is, well, you're basically independently for each parameter, you're asking a very simple question, which is, if I increase this parameter or decrease it, what would happen to the loss? Would the loss increase or decrease? This is basically what the derivative is, right? Like what would happen to the loss if I add an epsilon to the parameter? And you're asking this question independently for each example in a mini batch. For example, when we're doing mini batch of GD, and you get different answers, right? So some would say, it needs to increase. Some would say it would need to decrease. And you can think of this as a sort of as a tug of war, where each example is trying to pull of the parameter in one direction or another. And the way learning happens is you have all of these examples trying to push the weights towards themselves, and you reach some kind of equilibrium at some point. So you're playing out this sort of tug of war game, and you get some kind of equilibrium, and that's how learning happens. So what does that mean, and what implication does this have for learning? So what that means is that for learning to progress properly, you need to have, at the same time, or at least in expectation, you need to have all the examples present, right? If you're playing this tug of war game in order to learn, for the tug of war game to make sense, you need to have everyone that's supposed to play the game needs to be there pulling on the rope. Otherwise, the result will not be meaningful. And what would happen in a normal learning system is that actually not all the examples that we're learning are equally hard. Or if you're doing multitask learning, not all tasks are equal. So what might happen is that early in the learning process, you'd learn a big chunk of your data set, so you'll be able to perfectly predict sort of what is the right output for many of your examples. But because you have to enact this tug of war game, you still need to evaluate those examples, and you still need to compute the gradients of those examples. So like if I would, if I'm learning ImageNet, and I would say in the first step of 50% of the data I'm classifying correctly, if I'm throwing that 50% of the data out and just learn on the hard examples that are left, what would happen is, well, that part of the data, that mode of the data is not going to be present in the tug of war, and we're going to forget it. Catastrophic forgetting kicks in, and what would happen, you learn the hard ones and you forget the easy ones. And this is sort of how we lose a lot of learning efficiency and a lot of computational efficiency and potentially even data efficiency through the fact that, in order for learning to happen, we need to have everything present at the same time in order for HGD to make sense. And what is even more interesting is, we have sort of this understanding that there are easy and hard examples, and this is sort of what happened. And there are multiple papers that are looking at this for particular data sets and always show that any data set has this bimodal distribution of easy and hard examples. But there is even new evidence that even if you do, say, even if you have tasks that are equally hard, you still don't learn them at the same time. So this is actually quite an interesting result that I'm going to go talk a little bit more about it on the next slide. But basically, the outcome is that in learning, we learn modes of the data sequentially. But because of this tug-of-war dynamics of HGD, we need to have all of them present at the same time. So we're paying a huge computational cost. So what a solution to continual learning or a solution to learning things sequentially can do, it can help you get this sort of learning efficiency. You can get unprecedented learning efficiency by avoiding repeating things that you've already learned, by allowing you to focus only on the things that you don't know and sort of keep learning those. And then, to me, this is sort of a promise of continual learning that I think goes beyond the world is non-stationary and can sort of have an effect on all forms of machine learning that we're doing right now. So I wanted to talk a little bit about sort of these. So this particular paper that I like quite a bit, that's called the ray interference. So it's sort of the paper itself. It's more about deep reinforcement learning, though I think it applies to deep learning as well. And there's some prior work to this from Andrew Sachs about exact solutions to deep linear models that kind of hints that the same problems might happen in deep models as well. And the idea is, what we're showing here is that if you have two tasks that are equally hard, equally complex, and you're trying to learn them together, and there is any form of interference between them, then what would happen is that one task would take over the other. And usually this is decided by initialization. So there's some kind of symmetry breaking at initialization that favors one of the tasks versus the other. And then as soon as one task starts learning, because of the interference, it's going to push the other task down. So the end, the observation is, what you'd see is that you actually end up learning the task sequentially. And this happens more often than we think. So even though we have two modes of the data that are equally represented in the data, by chance, by initialization, and sort of due to the interference in between the data in these modes, you end up learning them sequentially more often than we think. And for DeepRL in particular, there's an additional effect where when you do this, what happens is you kind of introduce plateaus in the loss surface. So you end up with this kind of learning curves where you kind of, you learn, you stagnate for a while, and then you learn some more and you stagnate, in like almost like a waterfall kind of learning curve. Cool. So going back to the gradient-based optimization. So I guess sort of the thing that I wanted to highlight is that in normal machine learning, we're relying heavily on gradient-based methods. Gradient-based methods use this kind of tug-of-war dynamics to resolve credit assignment. And what I mean here by credit assignment is basically deciding which weights get to be blamed for which part of your loss. And this is sort of, this tug-of-war dynamics is what requires this ID assumption, right? And to me, at least, I think this highlights the fact that normal learning in machine learning doesn't have any form of explicit knowledge composition. So you're not composing the knowledge that you have. You're learning everything simultaneously by having this sort of tension between all the different things that you'd like to learn and trying to find this equilibrium. And whenever you fail to do this credit assignment, that's when you get catastrophic forgetting. So catastrophic forgetting is when you have this tug-of-war game and some part of the, some opponent is missing. And because of that, you basically forget anything that particular set of examples we're supposed to represent. I'm maybe exaggerating a little bit, and I love to kind of go into the details and the nuance of all of this. I'm just trying to do like a black and white picture, but I'm just sort of trying to explain why this can have such a big impact on normal machine learning in general. And the way I see continual learning, and this is sort of how I resolve all of this tension of like the different desiderata and what would happen and what protocol makes sense and what protocol doesn't make sense, is the way I think about continual learning is sort of a study of this credit assignment problem and a study of this tug-of-war dynamics. And then this kind of empowers me with different ways of understanding whether I'm making progress on the question that I care about or whether I'm not making any progress. And I think that's sort of the hardest part in continual learning is you can always tweak the problem slightly one way or another to give you the impression that you're making progress, but you never know whether the progress you're making would be meaningful for the community or not. And usually this stems from the fact that you're not very explicit beforehand of what aspect of continual learning you actually want to study and what exactly you'd like to solve. And yeah, I mean, now I kind of try to motivate a little bit why we should care about continual learning and sort of what are my personal view on why is important to do continual learning. And I wanted to say a few words about sort of where the field is right now. So I think, you know, as a subfield, continual learning is relatively new, but it's been growing really fast. So I've seen, you know, the workshops. So we now have workshops on continual learning, and the number of participants are growing exponentially, more or less, for the last few years at NeurIPS and different other conferences. And I sort of wanted to give for everyone like an overview of what we've been doing in this space. Again, I mean, just kind of highlighting again that you know, there are different protocols that you can have in a continual learning problem. All of these protocols make sense, and I think there's been a bit of discussion in the past of some protocols might be not being meaningful. I know that there is this continuous question of whether catastrophic forgetting is something we should care about or not. I think the answer to all of these questions is that all of these protocols make sense. The only problem is that they're looking at different things, and you need to be careful. You need to have this very fine-grained taxonomy of what are the different problems that we might care about, why we care about them, and where we might use the solutions. So there's a little bit of that you need to take into account, and that makes it really hard to compare methods between methods, because different methods, you know, do different kind of trade-offs that are suitable for different aspects of the continual learning problem. The other thing that I wanted to highlight is that you know, I'm going to like branch the solutions into 3 big categories, and this is sort of the standard way of doing it. This is how most papers that I've seen on the topic split the continual learning approaches, but there's a lot of commonality between these things, right? Like sometimes it's really hard to tell whether a method is, you know, of type A or type B, because it's actually just somewhere in between. And the last thing is, as I mentioned before, there are many subfields that are, you know, really close to continual learning, and you know, we have this issue with continual learning and lifelong learning, which are, I think, in my view, almost the same topic. But then you have things like meta learning, transfer learning, domain adaptation, never-ending learning, online learning, and so forth. And they all share a lot of this protocol, a lot of the structure, and a lot of the techniques kind of work in between these fields and are sort of inspired or just sort of taken from different places and brought into the continual learning space. So by and large, I feel that at the moment, what most continual learning solutions are doing, they're trying to imitate sort of the multitask solution. So there is an assumption that what's happening in continual learning is we have a bunch of tasks. Again, you don't always need the concept of task, but it's very handy when you're trying to be pragmatic and explain what you're doing. So if we assume we have a bunch of tasks that you have to see one after the other, the assumption is always tends to be that, well, if I would have all of these tasks together at the same time, and I could do the normal ID learning that we know, and which would just lead to multitask learning, this would be the optimal thing that you can do. And this is sort of what continual learning should be able to converge to, the same solution as a multitask solution. I don't think this is always true, and I might say a few words about this later on, but by and large, this is the assumption. So the idea in most of the solutions is, how can they mimic the multitask solution when you don't have access to all of the tasks at the same time? So in regularization-based methods, and a lot of these works are inspired by Bayesian learning, The big idea there is, well, if I write down the multitask loss that I would like to do, then there's some of these tasks that I don't have access to, like task A and B in this sequence where I have ABC. So what I'm going to do is I'm going to build up a new term, some form of regularizer that will just be a placeholder for these tasks, right? So like in this little animation that I have in the corner is basically the red guy, right? So the red guy is something that I build, and what it's supposed to do is supposed to be an approximation of the task that I don't have, and I can insert this thing in there, and then now I have back my tug of war dynamics. And most of the methods in this sort of family kind of follow this thinking. There's a lot more methods that are not cited here, like VCL and so forth. But basically what they do is they add some form of regularizer, and the regularizer takes care of the task that I'm missing. So this is a first big family of methods. The second family of methods rely on memory and rehearsal. And the idea here is quite simple, is just saying, okay, I cannot go back to interact with this previous task, but what I can do is I can store some examples from this data, and then I can use those examples. I can rehearse those examples to remember. And there is lots of comparisons with human, and when we dream and all of these kind of things, we have this stage where we kind of in our mind repeating things that we've seen in order for us to consolidate and fully understand what happened. And this is, of course, like a very rich space of things, and then there's like different kinds of ways of approaching this problem. So there's a question of, okay, if I am to store a few examples and I can only store a few of them, which ones do I pick to store? And this question of like compressing the data of the previous task that you have. And then there's the whole family of approaches that use generative models, where they say, well, I'm not going to store anything, but I'm going to train a generative model of the data that I've seen, and I'm going to use that one, and I'm going to use the samples from that model as sort of my data to train. I wanted to mention a little bit sort of the MBPA model that's there that does something slightly different, and I think it's kind of interesting because it goes back to this question of the multitask solution. So when we do this rehearsal, again, what we're doing is we're trying to imitate this multitask solution, right? We use a little bit of data for the task that we don't have, and to kind of imitate that particular losses. The MBPA does something slightly different, which is what it does is that assumes that what we have is we're going to have a parametric model that gives me like a starting point. And then every time I need to do inference, every time I need to answer, what I'm going to do is I'm going to look in some episodic memory and retrieve examples that are meaningful for that local context. And I'm going to, on the fly, quickly learn an output layer that makes sense for that particular point that I'm trying to do inference for, learn that, do inference with that model, and then throw it away. So there's this idea of like local adaptation. So every time I need to do inference, I need to first do some kind of adaptation to the particular local context, and then provide an answer. And the reason I think this is interesting is because it kind of avoids this question of whether there is a multitask solution. So sometimes you can have a bunch of tasks, A, B, C, that are contradicting each other. So one task tells you to go left, the other one tells you to go right. So if you try to imitate the multitask solution, what you get is you get a system that doesn't perform well on anything, right? Because, well, it's confused and it just doesn't do anything because neither left or right is good, because different tasks tells you to do different things. So MBPA, and you can think of MBPA as basically just taking a lot of inspiration from meta-learning and things like that. What it basically does is every time you need to make a decision, it tries to look at the data and it tries to infer what is the current task, what is the current local context, and based on that inference decides what to do. And this way you resolve this tension where, and you can come up with a system that can handle sequences of tasks that are opposing each other, right? Because it does this sort of local inference on the fly. The other thing that I wanted to highlight here in the memory-based method, just to kind of highlight the fact that these things are so similar. So as I said, a bunch of these methods rely on generative models. These are two examples of curl and the hybrid probabilistic models. So their work I was involved in at some point, and they're just sort of different. So the curl is relying on a VAE formalism. The hybrid probabilistic model relies on flows. And this is just a different ways of learning these generative models that give you data. But the interesting thing, in particular, in the last of works in the flow scenario, what can happen is once you have this flow, you realize that you can avoid the process of sampling data and learning on the data completely. And what you can do is you can say, okay, I have the original flow and I have the model that is learning right now, and I want to see that if I take a latent code push it through the flow, through the original flow, and then use the inverse of the new flow that I'm learning, I want to end up in the same point. And you basically kind of relying on the generative model in some sense, but you end up with a regularization term that is very similar with the first family of methods. And this kind of just shows you that you're sort of on a continuum where you kind of can move from rehearsal to regularization very smoothly. And there's other examples as well, like VCL has corsets and stuff like that, which again, kind of looks almost like rehearsal. And it's like a very continuous space between these two families of methods. And then the last family of methods, the way it's usually split in the literature is sort of modularity and sparsity-based methods. And the idea here is that you're kind of carving pieces of your model for each of the tasks, right? So you learn task one, and after you learn it, you decide, okay, you know, we know from things like the lottery ticket hypothesis and all of this other kind of studies on generalization and sort of learnability in neural networks, we know that we tend to be extremely over-parameterized compared to the size of the solution that we actually need to solve a task. So what we can do now is we can identify that subset of the model that's actually useful to solve the current task, freeze that, and somehow reuse the rest of the capacity to learn new things. And most of these methods, you know, depending on the methods, you know, there are many variations on this, but that's sort of the scheme, right? It's kind of building these modules one after the other, where each module is supposed to map to like different tasks, or if you want, like different distributions, as the distribution keeps changing. I think this is just as a I think this is the family of methods that is probably less explored compared to the other two, but it's probably the most interesting one. So I really hope that in the next few years, we're going to see a lot more work in trying to understand the interaction between modularity, sparsity, and continual learning, and sort of learning in non-stationary settings. I think it's a somewhat underexplored part of the problem. And yeah, then like, this is sort of gives you like a high-level view of like what are the different methods and what are the way people are thinking about this continual learning problem. And what I wanted to move on from that is to discuss a little bit, okay, what are these methods applied on, and what are the implications of these benchmarks. And as I said, like benchmarks and trying out continual learning, it's one of the biggest problems we have right now in the subfield. So we don't have, I mean, we have very well-established benchmarks, but there are many problems with those, and problems that basically everyone in the community acknowledges. So it's not like, you know, everyone acknowledges. We've been discussing these topics over and over again at every time we meet at any of these workshops. The only question is it's kind of hard to move on. It seems it's a bit harder for us to kind of agree what is the next big thing that we should run things on. But just to give you an idea, so that the kind of benchmarks that we typically use, so these are a lot of time vision-based, just because they're so handy and easy to use. So you can take your favorite vision data set. You know, MNIST, I think MNIST right now is not used anymore. Maybe MNIST is too easy. There's some scenarios where MNIST is still good. But then, you know, you go CFI, ImageNet, OmniGlot, whatever, SDHN, whatever you prefer, and then you split the data distribution into modes, and then you kind of just see the modes one after the other. So this is the sort of split variant, which can be applied to any data set. So you just split along classes, and you know, I mean, you get all these kind of variants of like class incremental and so forth, variants of continual learning. But in big strokes, that's sort of the idea of the split variants of continual learning. And I guess permuted MNIST kind of stands out because it's a task everyone kind of runs on at some point or another, where you don't actually split the data itself into groups, but what you do is you use random permutations of your pixels as new tasks. And the advantage of doing that is you can generate arbitrarily many tasks. So usually when you see a paper that says, oh, I've run this on 300 tasks, it's usually permuted MNIST because it's so easy to generate 300 tasks in a row. But arguably those tasks might not be sort of the kind of task we care about. There's been some effort in trying to move continual learning sort of in the RL domain, and I've been involved in some of these efforts. But even there, like it's usually done in a very clunky way. So you have things like Atari, and people did this on DM Lab, and we've tried to do something like this in StarCraft as well, or other domains. But usually what you do is you know, like if you take something like Atari, which is the one that's best studied, you pick these games, you pick a bunch of Atari games, and you put them one after the other. And the issue with this, and potentially issue with the previous benchmarks, is the whole sequence of tasks is, it's to a large degree very arbitrary, right? So there is no direct understanding of what is exactly transferable from one task to another, why you'd even do them in this kind of sequence, right? So this is just sort of arbitrary sequences of tasks that are of variable difficulty, and the focus is the system needs to handle them somehow and needs to be able to learn them. And then once you've set up your benchmark, whatever it is, the typical plots you do. So I took this out from EWC, but most papers would end up making plots like this. Is you're looking at the average performance on all the tasks, and you have that your method is doing better, or you're specifically trying to focus on catastrophic forgetting. And I think this is sort of one of the main criticisms that people usually have to papers in continual learning, is the over-reliance on catastrophic forgetting. So the first thing that everyone looks at is, like how much does my system forget when I learn new tasks? And I just sort of want to re-emphasize that actually this is not the only objective of continual learning. So at any point in time, there was never said that, okay, continual learning is about resolving catastrophic forgetting. Continual learning was always about, resolving catastrophic forgetting in a way that gives you forward transfer, and you have a fixed size model and all the other desiderata that I've enumerated at the beginning. But by and large, catastrophic forgetting seems to be the thing that kicks in first. So it's the thing that you see immediately as you start to running on a sequence of tasks. And somehow most papers and most of the community kind of ended up focusing on solving this catastrophic forgetting problem, in the expectation that we can solve this and then we can move to the next one. But as I said before, I think this is extremely problematic because this desiderata is actually in tension with each other. So there's no sense in which you can say, okay, I've solved catastrophic forgetting, this is solved, I'm going to fix this, and I'm going to start solving the other bit, and kind of just combine the solutions as we go along, because there's no combination. Like when you start combining them, that's when you start needing to do some kind of trade-off. So you need to allow yourself to forget some in order to learn faster, or something like that. Okay, so this is sort of usually the kind of plots people do. Sorry. And then you can I guess you can then try to plot this is like a set of methods, and you can try to plot these models and see sort of what they do. And I think I'm going to explain the table a bit later, but I think one thing that comes out at the moment from most of these continual learning methods is that we've become pretty good at dealing with catastrophic forgetting, right? So performance is there. It sometimes feels it's kind of neglected in the field, but sometimes it feels like we're losing a bit of performance, or how much generalization. So we're losing some plasticity, it seems, in practice. Is usually not much, but probably it's still extremely important. But forgetting by and large is solved. On the other hand, if we're trying to measure any of the other desiderata that we might care, so in particular here we're also looking at forward transfer, we notice that basically any method that does well on forgetting, it does worse on forward transfer. So it's a direct trade-off. At least in the methods that we have right now, it seems we're doing a direct trade-off between speed of learning and sort of the ability to remember, which is actually not what we wanted, right? So the intuition that we started, or at least the story that I was trying to tell you, is that in continual learning, the whole point is you build on the knowledge that you acquire knowledge from one task to another, and you protect that knowledge, so you always remember what you've learned. You've learned a bunch of skills, you remember those skills, and then when you see a new task, you can build on those skills, so you can learn faster. And it feels like exactly the opposite it happens. Just because you're maintaining the skills, you can't learn, you can't learn faster, and you can't learn as well either. So you're basically sacrificing everything in order just to remember these things that you've learned. In the minutes that I have left, probably roughly something like 20 minutes or so, I wanted to start discussing of like a way forward maybe for this. So this is sort of a benchmark that we've recently worked on, and maybe a way of thinking of the problem. So I think what's important when you're trying to set up this kind of continual learning benchmarks, it's important to have an understanding of what is it that you're doing, why you're putting this task together, what is the goal, what is the best you can hope to achieve, what is the worst you could achieve, and where are the methods that are out there already. And in particular, when I was thinking about these things, we came up with this story that we call the distractor problem. So the idea is that whenever you learn in a sequential way, and assuming we have tasks just to make things easier, the paper is actually on archive. The slide is a bit old. You have a sequence of tasks, A, B, C, D. And one thing that happens more often than not is that a task starts behaving as a distractor. And what that means is that if I'm looking at a transfer, the naive transfer between A, B, B, C, and AC, I see, I think I have a plot for this just to make it a bit clear. You get sort of one of these kind of transfer matrix where you say that, A is helpful for C. So if I learn A and then I learn C, I tend to learn C much faster. A might be or might not be helpful for B. I think that's a little bit less important. But then B is harmful for C. So if I learn B and then learn C, I actually learn C much, much slower, because somehow the task B and C, they don't like each other, right? They tend to use different features. They tend to interfere with each other. So if you pre-train on B and fine-tune on C, you have this negative transfer. And the idea in this work, in this distractor problem setup that we're setting here, is that we want to use this transfer matrix as a way of talking about the similarity between tasks. So this is a very hard problem in the field, and there's different papers on it and different views on it. But in general, when we have two tasks or two data distributions, it's really hard for us to talk about how these two distributions are related. You have very simple metrics like KL or whatnot, but those are not necessarily informative, and it doesn't really tell you that, okay, if I have a particular model, how much would this model be able to exploit the common structure between A and B? So this is something that people talk a lot about it. So the causality seems to be a tool right now that people tend to like to use for this and say, oh, if there's like common causal structure between A and B, then this is related, and sort of that common structure tells us what is the commonality between tasks. But I would argue that with the models that we have right now, so if you'd end up training a ResNet on those tasks, this causal graph is actually not informative at the moment, because the way ResNet learned the solutions is somehow not relying directly on the causal graph. So you need to go deeper and build a solution that directly relies on the causal graph, which it's sort of a different direction, which is also extremely interesting. But at the moment, for the architectures we tend to use in practice, the architectures that really do tend to perform well and are generic enough to apply to sort of data for which you don't have very explicit prior knowledge of exactly sort of where the data comes from, it's really hard for us to tell the similarity between tasks. So the idea in this distractor problem is, okay, just to use the transfer matrix to kind of give you a sense of similarity. Now we have this transfer matrix. Now what we can do is we can create a sequence where we can look at distractors. We can add a distractor in the sequence, like B in this particular case, based on how things happen when they transfer, and then say, what we would really like is to have this kind of magical continual learning solution that will be able to learn A, B, C, and it will be able to mitigate the interference that B induces. And we're not even looking for like the best case scenario here. So we're thinking about like a realistic target, which would be like, what I want to do is learn A, B, C, and then C as fast as if A was the task I've pre-trained instead of B. Right, so you could have compositions of transfer. So it could be that if you had, many tasks before, it could be that you can compose how much forward transfer each one has. But for now, we're just setting as a target, like transfer as much as sort of the best of the previous task. And this is sort of just a target for us. And we wanted to do this sort of in a realistic scenario. So we've made this paper. So now you have the link that should have been on the previous slides as well. So we built this continual meta world, or continual world, and it's basically what we wanted. We wanted something super pragmatic that people can use. So we went with a benchmark that's well established, meta world, and it's cheap enough that people can easily run, but sort of still interesting enough to see some interesting structure. In particular, still interesting enough to kind of see this kind of distractor behavior. So we're trying to move away from things like Atari, where like it's actually quite, the tasks themselves are a lot more challenging, and sort of the transfer matrix is a lot more noisier. And what we do here is, you compute the typical metrics, so you can do average performance forward transfer and so forth, and for getting. For forward transfer, you just sort of look at the area under the curve, and you're asking yourself, how much faster am I learning now if I did pre-train? And then you can compute sort of a transfer matrix like this, and use that transfer matrix, and now you can construct the sequence And now you can construct kind of like a reference transfer, which is if you had a distractor, ignore the distractor and tell me how much you'd have transferred if you didn't have the distractor in there. So this is sort of what this RT number is. So again, as I said, this is not an upper bound. So it is possible for continual learning systems to do even better than this, but it is like a reference transfer. It is like a target for us to see whether we can even achieve this. And for the data set we have, this gives you some numbers, 0.4 in this particular case, 0.46. And the idea, what we've done in this paper is we just took existing methods, we ran them. So this is a table you've seen before. And what you can see is that at best, you can do as well as not using any continual learning system if you're just looking at forward transfer. And that is 0.2. So about half of what this reference transfer would do. So that is still heavily, heavily penalized by these distractors. So I think this is kind of just tells you like, okay, what are the difficulties in sort of the systems that we have, and particularly like now, because we're focusing on this idea that we want a continual learning system that is able to build on the knowledge that it has and kind of use that to learn faster. It kind of shows you that the solutions we have so far, they're not doing that. So they're good at dealing with catastrophic forgetting, which is fine, but they're not dealing with catastrophic forgetting in sort of this kind of way that allows you to actually exploit whatever you remember in order to learn more efficiently things that come after. It actually does the opposite. So almost all solutions to catastrophic forgetting that we have now forces you to pay a continual cost. You know, it's like they many times it's a computational cost, but it also like prohibits forward transfer in a direct way. And this is sort of what you can see from the table. So this was, I guess, a discussion about sort of the weakness of evaluations, especially sort of the original kind of benchmarks that we used, which were kind of random sequences of tasks where, you know, you'd run continual learning system, you'd focus on catastrophic forgetting. There was a note I wanted to make again. So why wasn't this such a big thing in the past on the previous benchmarks? And I think part of it is if you take something like permuted amnesty, so if you take some of these tasks, it's actually completely unclear whether there is anything to transfer at all. So then, you know, even if you compute the forward transfer number, that will be close to 0, and it will be close to 0 for all methods because there's nothing to transfer. So then obviously your eyes go to catastrophic forgetting, where you see a huge gap and kind of dominates the whole thing. So it's sort of important to have the right benchmarks that highlights the part that you'd want to explore. And again, as I was saying before, this is not saying that the old benchmarks are not good or the methods that we have are not good. It just depends on what question you're asking. So the particular question we were asking here, which is remember things in order to reuse them later, that's not being answered correctly at the moment in continual learning. The other thing I wanted to highlight quickly before I finish my presentation is something about another issue with continual learning, which is sort of in my view, reliance on overparameterization, and it's sort of a kind of a thought question whether this is a good thing or not. So just briefly, what we've done here is we took many of these kind of typical benchmarks like CFAR, mini emissions, and so forth, and then we look to see. So we use this mode connectivity. So some of you might know there's this idea of looking how two solutions are connected to each other. So this mode connectivity stuff, and we're looking to see how the multitask solutions, which we assume are the best thing you can do in continual learning, whether they're mode connected and how are they mode connected. And what this paper kind of like, what this experiments kind of find is that for most of these benchmarks, all of the solutions that multitask give you, they're linearly connected. So another way of phrasing this is basically if I learn task 1 and then I learn task 1 plus task 2, I find a solution for both tasks. And that solution is within the region where the second order Taylor expansion of the first task holds. And then this is interesting for two reasons. One, it basically says that regularization-based methods, which in the literature, if you kind of skim through recent papers, are kind of seen as being inferior to rehearsal-based methods. They technically can do as well because the core they're seen as being inferior because they're making these very strong assumptions about, okay, I'm going to take a second order Taylor. I'm considering that the posterior is just a Gaussian. So these are technically seen as very strong assumptions on the structure of the loss surface. It seems these assumptions are good enough, right? Because multitask doesn't take you somewhere where these assumptions don't hold for most of these data sets. So this is one observation. But the other observation that I think to me is also important is the reason you get this kind of property is because we're in an extremely over-parameterized regime. So somehow the over-parameterization comes into play. And if you reduce the parameterization, like these things don't happen as well. And this is sort of a very generic thing, right? Like if you take ResNet and ImageNet, that model is over-parameterized. And over-parameterization seems to be key for a lot of the results we have in deep learning. But the question is whether this is something we want to heavily rely on. So in particular, if you think of a lifelong learning scenario where the distribution keeps changing, and whether you're trying to remember all this kind of previous distributions that you don't see anymore, you might quickly end up in an under-parameterized regime, or you can end up in a regime where you don't have this over-parameterization to help you. And the question is, what happens then? Do all the methods that we have that seem to be doing so well, are they all relying on this assumption? And actually, if we push them in an under-parameterized regime, will they all break? And do we even need to address this problem? Is there a way of addressing it without making our system under-parameterized? Sorry, this was a last slide on the same thing, but it basically just showing that you can use this mode connectivity, and it's very reliable, and this sort of works as well as any other method for the typical tasks that we see. So this is more saying something. This potentially is saying more about the benchmarks than saying about the methods. It's basically just saying, the benchmarks that we have, they're such a nature, and the model we use are so over-parameterized that actually this kind of very simplistic assumptions like second-order Taylor approximations, Gaussian posterior, stuff like that, they seem to hold perfectly for even after we see, just to be clear, even after you see like 20 tasks in a row or like 50 tasks in a row, you still can do a second Taylor of the first task, and everything is within close within that really region where this approximation holds. And now I hope I'm not over time. So this is, I went through a bunch of works, but there's a lot of people I worked with. I just wanted to, it's been a really hard year now, 2 years almost for everyone. So I just wanted to give a big thank you to everyone I've collaborated with in the last, 2+ years. And I'm sure there are many people that I forgot, but none of the things that that I managed to do would have happened without the help of others. And just wanted to say thank you, and whether there are questions about the presentation. Yeah, so if anyone has questions, do please write in Slido. So that's sort of the main mechanism for us to see the questions. So put your question in Slido, and yeah, I'll be able to. Okay, so I can start looking at the questions. So the first question appearing here is, are we going to see more formally? Sorry, I need to make this a bit bigger for myself so I can see. Okay, so are we going to see more female presenters and people from other underrepresented groups? Is this particularly related to the workshop? So if you look at the workshop, I mean, we already have the list of the speakers, so you can see directly who would be speakers. In terms of female presenters, we've always strived to try to be as balanced as we can, both for this workshop, but also for most of the events that we've done in the past. And I think this is a tendency now in the field as a whole. It's a sort of a slow process, and it takes time to get there. But definitely, I think almost everyone I know of organizing all kinds of events, even like the big conferences, for them, this is a very big topic and something that everyone pays a lot of attention to. Cool. So this was the first question. For the second question, what is differentiating point between continual learning and lifelong learning? So depends on who you're talking to. So in my mind, I do feel like these are kind of asking the same questions. The typical answer that someone would give you is lifelong learning has a bigger emphasis on a really large number of tasks, while continual learning experiments tends to be with a smaller number of tasks. As far as I know, this is sort of the big thing that maybe people bring up. But I think it's a very superficial difference, and actually we all kind of care about the same regime. So yeah, hopefully that helps. How important is graceful forgetting in CL system? What methods could help? Yeah, so this is a very good question. It's something that people have been discussing. I've been thinking about it a long time for a long time as well. I do think graceful forgetting is really extremely important for CL systems, right? It's a way of kind of controlling this trade-off between forgetting and transferring capacity and all of these things. The issue we've had in terms of like, if you just look through the literature and you try to find papers that are talking directly about graceful forgetting and providing methods that deal with graceful forgetting, you won't find many of them. And the reason for that is, and from my personal experience, we've actually came up with a method for graceful forgetting, and then we tried to use it in one of the existing benchmarks, and it just doesn't make a difference. So I think part of the problem is we need to have the right settings for us to exploit this graceful forgetting. When we go to a really large number of tasks, we end up using something like permuted MNIST, and I don't think that is the right problem. So we need a much more natural setting where you can have hundreds, maybe thousands of tasks that are difficult enough and interesting enough for you to use, like you know, modern deep learning tools and kind of deal with this graceful forgetting problem. But by and large, it's super important. Everyone agrees. We just need to find it a way that it's much more practical to actually do experiments on it and publish works on it. But yeah, it's a very important theme for continual learning. Okay, so for the next question, are you familiar with the applications of continual learning in industry? So I'm not that familiar, and I would be definitely interested to understand more. Like, so the issue with continual learning, I think, in industry, or at least my understanding, is that we don't necessarily have tools that work well enough that would be applied. We definitely know setups where it would like naturally be a solution. Like we know, for example, that you know, whenever you have, I don't know too much about recommender systems, but for different various systems, you know, you have data keep coming in, and what happens more often than not is, you know, the solution that they have is thrown out, and a new model is to retrain on the old data plus the new data, and you keep doing this regularly. And this is kind of expensive and computation intensive, but you can parallelize it, run it in the background, and a lot of big companies do this for a lot of things that are out there. And we'd really like not to do that. We'd really like to just kind of continue training the system that we have. There's also people who try to just fine-tune the system, as far as I know, and there's good reasons for that. If you just fine-tune it, you kind of lose performance. So you really need to throw the system away and retrain it from scratch. I think it would be nice to have a continual learning solution that really, you know, can work in that setting. I don't know whether they're there yet, but I think the issue is having like a benchmark where we as researchers can work on, but where the solution can directly be applied in industry, because I think it's kind of hard to kind of motivate the researchers to work directly on applied problems that are, you know, sort of hidden under the hood. And if they work on that, again, that's something you publish on, and people would not know you work on. So yeah, I think we're breaking that barrier, coming up with a huge benchmark that's interesting, that is approachable, but it has like direct application in industry. I think that could boost the field quite a bit. And there are people thinking about this, and there's some proposals out there, but I don't think there's yet one that kind of took over the field and everyone is saying, okay, this is the challenge, this is what everyone should be doing. Are there other approaches to detect distractor tasks? So, I mean, that's a good question. I think the way we define distracted tasks is through this transfer matrix. And this is because we needed some kind of similarity metric. At a high level, conceptually, what we're talking about is if there is, you know, we're talking about similarity between tasks, and we're talking whether there is, you know, a task that is not similar to another, that would kind of induce the distractor. But yeah, pragmatically, I think transfer matrix, to me, in my mind, is the most reliable way to detect whether there is interference between two tasks. There are some works on task similarity out there, but again, they tend to make some kind of strong assumptions. There is even benchmarks that are using sort of causal graphs to kind of define the relationship between tasks, and then you can use that and define sort of what the distractor is according to that. But the question is, so my experience is when you train systems, like the kind of transfer, the kind of learning you see depends heavily on the architecture you use, the optimizer that you use. It's not just about the data. So I'm a bit skeptical about sort of similarity metrics that don't take into account the model and the learning process when they compute the metric. So I don't know how reliable they are. Okay, next question. Extending the previous question, what about online learning? So online learning is very related as well. There's a difference, again, I think it's a difference of communities, a difference of focus. So a lot of online learning work is done in a, a lot of online learning work is being done in a more of a theoretical framework. People really care about bounds there, which is something we don't really care about continual learning. And in the online literature, a lot of time people really avoid using systems for which you can't compute regret bounds and stuff like that. So they tend to use like linear models and other kind of, so that's, in my mind, that's superficial, but it is a difference, you know, the tools that they use, the community, the kind of papers you can write, the kind of reviewers you can expect, right? So it's about theory, it's about regret bounds and stuff like that. While continual learning is not that much about that. But the other thing is, forgetting is not that big of a theme in online learning. There is ways of formulating the online learning problem to have forgetting in there, but it's not sort of the mainstream one. But otherwise, there's a lot of similarities. So you can take even algorithms like EWC, and you can find some of the roots, or you can find a lot of similarity between these algorithms and some online learning algorithms. So that definitely there is a lot of commonality between this, and I don't think it's acknowledged all the time, and I don't think we have enough online learning experts working in continual learning or enough continual learning people trying to do online learning. So it would be really nice if we get more of that. Okay. Okay, so could the distractor problem pivot to be a cybersecurity issue in non-deployed CL system? Yeah, the attacker intends to disrupt the running CL model by sure, it could be exploited that way. That's a very interesting and nice way of phrasing this. You could definitely, like, I mean, assuming that a system, like if you are to think about pragmatically nowadays, assuming that a system is continuously fine-tuned, which is the most likely thing, you can definitely exploit how you can, you know, how you can affect locally the distribution of the data that the system is seeing, such that you kind of make it forget arbitrary things from the past, or basically even catastrophic forget and breakdown. I haven't seen any work looking at this directly and discussing sort of how you would exploit this. I think it's a really cool perspective. But yeah, definitely, it would be nice to see. I mean, I guess now here, like, there is a lot of strong assumptions, right? Like, you need to make strong assumptions about how the system learns, whether it learns continuously, whether it's a static system that, you know, throws data away, stuff like that. But yeah, if you assume a system continuously learn, you can definitely play this game. And this might become a really interesting problem for things like self-driving cars and so forth, if they tend to adapt, you know, after, you know, adapt to the driving that you do and stuff like that. Then you can ask, okay, how can you break a system like this? That's a really good point. Cool. So I think we don't have time for questions anymore. So I want to thank everybody, and I'm on Slack. So if you have questions, yeah, I'm happy to keep answering them on Slack.
Excellent. Thank you, Razvan. And as Razvan has mentioned, for any of the follow-up questions, please do ask them on Slack. They will stay on Slido for another 10 minutes or so, and then we would very much encourage you to continue the conversation with Razvan on Slack, where you can ask more questions, have in-depth conversation throughout the workshop. So please do use that opportunity. Now, with us running short on time, we are going to have a few minutes now for a Vinted quiz, where you will be asked 3 quiz questions. Please do use your name and last name so that we're able to identify who wins the quiz, and later on send you the books or reach out to you. So we are going to start the first quiz right now. Just give us a second, we're going to run it. It should pop out. Yeah, so join the quiz. Please join the quiz with your real name. And we'll start the quiz soon. People are joining, we see. Excellent. There will be 3 questions, 3 quite simple questions, but tricky questions, which you can answer. And then we will contact the winners to award the books, or you choose the books. Yeah, and we will need a screenshot of you winning it so that we can actually check that it was you who won it. Yeah, so please do save the screenshot. Okay, a lot of people joining. Excellent, excellent, excellent. Just a few more minutes and we're gonna start first 3 questions, just 3 questions during this break. And for each question, you will have around 10 seconds. So it's quite fast. So be prepared. And you're going to win either a pattern recognition and machine learning book by Bishop or counterfactual and causal inference book or reinforcement learning book. So quite a nice 3 books. We do want to encourage the communities to kind of grow and educate one another. So please do join. All right. And I think we're about to start the quiz now. We have quite a few people. So let's go ahead and start it. All right. So which one of these is not an SGD optimizer? Just one correct answer. All right. Excellent. Now we are moving on to next question. Which one came first, Theano, Keras, TensorFlow, or Chainer? Excellent, excellent. And now moving on to the next question, and then we are going to have a break. Now, I remind you that the winners will be announced at the end of the event. So now we are going into the break and we are going to record all of the winners. And oh, there is one more question, sorry. And we're wrapping up with the final question. And now we're going into the break. Hi everyone, we are back. Hopefully you had a chance to use the short break after the quiz. And the next speaker now is going to be Viorica from DeepMind. She's also a co-organizer of the EML community. So we are welcome and happy to hear you, Viorica.
Okay, thank you, Jeff. So yes, Viorica Patrochan, that's my full name. I'm a research scientist in DeepMind, and just to say a few words about myself before going a bit into the research that I do. So I did my undergrad in Bucharest, in Romania, in computer engineering. Then through Erasmus program, I got to Toulouse, and where I did a master's and a PhD, mainly focusing on applied maths, but with focus on 2D image processing. And then I moved to Paris and Cambridge for a postdoc program, where I did research on 3D shapes and videos. And since 2016, I've been a research scientist in DeepMind and organizer of EML since the beginning in 2017. So yeah, as you can see, I've been working for quite a while with the visual data in different dimensions. So starting with 2D images and then going to 3D shapes and videos. And I could say probably that I'm a bit obsessed with the idea of solving vision, whatever solving vision means for everyone. So for me, solving vision means building a computational model of the human visual system. And of course, there are lots of practical applications that emerge when we have such powerful models. You can think of robotics, virtual reality, autonomous navigation, helping the visually impaired, and many more. But for me, this field is also very fascinating because I think it also allows us to learn more about how our brain works. So today I will cover a few different aspects related to video processing. So I will first motivate a bit why looking at videos at all. Then I will go through, I will cover a few popular video models and then mention a few efficiency challenges in video processing. And then ways we can address those challenges. So by looking at the learning paradigms, for example, using multimodal learning or self-supervised learning, and then focusing on a topic that is a bit more exotic, let's say, less explored, where we look at depth parallel models. And I will talk about how we can do depth parallelism at inference time, at training time. And I will also mention a few aspects of biological plausibility of backpropagation. And I will conclude with a short summary and let's say my vision for vision. How do we solve vision in the long term? Okay, so let's get into it. So why should we care about videos? So most of the successes in machine learning recently have come from image models. So you're probably familiar with ResNet 50s, and AlexNet was the very first the first image deep network. And more recently, we have the Vision Transformer, which are all very good at certain tasks on 2D images. And then if we have such powerful image models, the simplest video models that you can think of is nothing but an image model applied frame by frame on the consecutive frames of a video. So this is what I'm showing here on the left. So on the horizontal axis, we have the time or the consecutive frames of the video, and then on the vertical, we have the different layers of the network. And we pass each frame through the network, and we get predictions for each frame. And each frame is treated as an independent observation. So during training, one iteration could take in either isolated video frames, or it could take the entire sequence and average the predictions over time to obtain the prediction. Now, the downside of this kind of model is that it cannot integrate temporal information. So you cannot reason about motion features, for example. And in addition, you cannot exploit temporal redundancy to improve efficiency. And yeah, these are the kind of things that we will be looking at today. Now, with this kind of frame-by-frame video model, as I said, they work reasonably well. But for practical application, especially, they can pose important problems. Like, for example, you might notice here this kind of flickering effect. So you have some parts of the frame that are labeled correctly in one frame, but the next time step the label changes. And visually, it might seem, oh, this is a nice output, but in practice, this might not be good enough. Like when you think of self-driving cars, if you have a pedestrian that appears in a frame and then disappears and then reappears and so on, this could be difficult to deal with. So whereas when you would have a full video model that takes into account the temporal aspect and imposes temporal consistency, that should alleviate this kind of issues. So just to maybe convince a bit why it's important to reason also about motion, like this is the advantage that we get from videos. I'd like to mention a study that was done on humans, on patients recovering from blindness, like later on in life. So at that moment in life, they were already able to communicate, to speak, to say what they were seeing. So these were people like at 10 years old or 20 years old, and they had surgeries for correcting their vision problems, and then in the recovery time they were shown different kind of images to test their visual abilities. So they were shown the kind of images that I'm showing here in this slide. So, for example, you just have some simple objects, and then they were asked, how many objects do you think there are in different scenarios? Like you have separate objects, you have overlapping objects of different colors, and so on. And they were also shown like natural images, like you see here, a cow, and they were asked again, how many objects are there? Do you recognize the object? And so on. So importantly, these people had experienced this kind of objects through their other senses. So they had touched in their life a cow. They had they knew what a triangle is from their knowledge. And when these are the kind of results that they obtain. So here in light blue, you can see the control group, so people who have normal vision. So for them, all these questions are very, very simple, and they do perfectly well on these tasks. And then we have different patients that were in recovery. So we can see that when the objects are separated here, they all answer correctly. There are 2 objects there. But as soon as we start having overlap between the objects, or we have different colors, or they are asked to reason about depth, then they start to struggle. So they cannot give the correct answer. The same for the natural image. When they are asked, they don't recognize the object, and moreover, when they're asked to say, okay, how many objects do you think there are, they're just tracing the contours of the object and saying that, yeah, there might be, I don't know, 4 or 5 different objects there. Now, another type of images that they were shown is when they had motion attached to the pattern that they were observing. So now they have again overlapping objects that I've shown before, that they were struggling when the objects overlap. But now these objects started to move. So they would have different motion patterns. They would move in different directions, or they had objects with background clutter. But again, the object would have some consistent motion. And then in all these situations, the patients actually really improved their prediction once the motion was there. So they were able to perceive the motion, and this proves that motion is really important when learning to see. It's really important to recognize objects and to disambiguate the visual scene. So yeah, this is maybe a long story to say why I think the videos are really, really important in learning good models for the visual for our visual world. So a second type of model it's still really based on image models, like 2D image models, and then we attach an RNN to it, an LSTM, your favorite recurrent model, and then this can integrate information over time, and then it can learn to reason about temporal features like motion. So let's say this is an improvement over the simple 2D image model that we would just apply frame by frame. The downside to this one is that it needs large memory for training with the backprop through time. A different model that is very successful in terms of memory is based on 3D convolutions. So basically here we consider the video as a volume. So we stack the frames of the video along the time dimension, and then we use 3D kernels and we convolve our video volume with that to obtain activation maps. Now, importantly, these 3D convolutions, they are not they're not causal, because the temporal receptive field of the convolution operator is symmetrical in the temporal dimension. So to compute the activation at time t, we also have to look into the future. This can be made causal using masked convolution, but yeah, there's some overhead in terms of computation. So they are accurate, but they are not ideal, let's say, from an efficiency perspective. And there are quite a few 3D convolutional models that were very successful. So I should say these are successful for offline processing of videos mainly. So and they use they're based on 3D ComNets, and they use temporal striding, and in some cases they also use rely on inflated 2D models. So you do transfer learning. You have these image models that were pre-trained on some, maybe an ImageNet or some other data set, and then you just replicate, you just tile those weights over time such that you can apply that in on a video. So this is I3D model, for example, which is inspired from Inception, extended to videos. Another nice model is this one, for example, a slow fast model from Facebook, which has some inspiration from the human visual system, where they have this kind of two-stream system, one that looks at the video at a low frame rate, one at a high frame rate, and then combines activations. So in the same way that it's useful to reason about images at different scales, like different spatial scales, this model extends that same idea in time. So you use different temporal resolutions and extract features like richer features that allow you to perform a task. More recent family of models is based on this on self-attention. So the vision transformer is it's now a very hot model, is the hot topic. So basically, this model challenges the existing convolutional approaches and the inductive biases that we were using related to translation invariance and locality. And this model is inspired from the language community and treats image patches as tokens or words, and then uses self-attention to learn dynamic weights that can put more emphasis on particular parts of the image that are more important for the given task. So in this model, every patch can attend to every other patch in the image from the very, even at the very shallow layers in the network. So locality is not used as much as it is in ComNet. Although, yeah, let's say like the very first step of patching the image is still equivalent to a conv layer with large kernels and stride equal to the kernel size. So based on this successful image model, there were a few papers that proposed video models based on the exact same design ideas using self-attention. So they just, let's say, extended the tokenization to the temporal dimension. So several proposals for video models were published, but importantly, they all rely on pre-trained weights from the image model, so from VIT extended to video, because otherwise the training can be quite unstable. These are very heavy models. They're large models. They need a lot of training data. So starting with pre-trained weights from the image model really alleviates the learning difficulties. So here, for example, in this paper, the model here is Timesformer. They compare different ways of applying self-attention. So you can apply self-attention only within a frame and then aggregate over time simply, or you can actually do self-attention over within the frame and over the time sequence. So yeah, they've investigated the different dimensions, how to extend the self-attention to the time dimension. And they obtained very, very good results on different benchmarks in video processing. Now, we've seen these models. They achieve good accuracy on certain tasks on videos. However, there are quite a few challenges related to training such models and running them as well. So first of all, going to supervised learning, the labels are of course expensive, and in the same time they can also be quite ambiguous sometimes. Like, how do you choose the granularity at which to label your data? What are the right classes to consider? Will this, because if you train on a number of classes, will this transfer well to some other task that you want to solve later on? If maybe there you have a different classes. So there are all these questions, and yeah, I think the part with the labels being expensive is a major issue. So here I've also summarized a bit different challenges when it comes to latency, throughput, and memory requirements, and also the notion if these models are causal or not, because all these aspects are very important when we talk about real-time applications like robotics, autonomous driving, VR. All these require real-time execution. So yeah, like in a glance, we can see that, as I mentioned, the frame-by-frame models, they don't have very good accuracy, whereas as we go to temporal models like 2D that are based on RNNs or 3D ConvNets or video transformers, the accuracy keeps improving. However, this reverses a bit when we talk about latency and throughput. Of course, latency and throughput are better for frame-by-frame models and RNNs, whereas the larger models, the 3D ConvNets and the video transformers, they're very heavy, so their latency is very high. And yeah, you have here also, like in terms of memory, again, the 3D ConvNets and video transformers have high memory requirements. In terms of memory at test time, which is also very important, of course, like this image-based models, they are more efficient. In terms of energy efficiency, I think they're all pretty bad. Like if you'd like to try making a comparison between a GPU and how the human brain works and how much energy the brain consumes, you will quickly see that a GPU that runs maybe just one object detector consumes about 10 times more energy than the human brain, whereas the human brain does so many tasks in parallel. And yet it consumes so little energy. So there's clearly a lot of things that we need to improve about our systems to achieve like good energy efficiency, which is so important for embedded systems, especially. And then when we talk about causal, of course, again, we have the frame-by-frame models and the RNN models being causal, whereas the 3D ConvNets and video transformers, they are not causal. So a problem with these models is that the latency and throughput, they're dependent on the depth of the model. So if we wanted to increase the depth to get more accurate predictions, then this would automatically increase the latency, which is a downside. And of course, for video transformers, because of the self-attention mechanism, they have quadratic complexity in all dimensions. So this is a huge limitation when we think of processing long video sequences, for example. Maybe I hope you can see this in your display to understand a bit why latency and throughput can be problematic for applications. So here on the left, I'm showing a video at normal frame rate, 25 frames per second, and on the right, I'm showing the same video at 5 frames per second, which would be kind of the frame rate at which our detectors can run now, like our models can run now. So I can tell you that on the right, you see the tennis ball in only 1 frame. So I don't think you can actually play tennis if you were to see the ball in only 1 or 2 frames. So of course there are many works to try to improve these the downsides of these models, and they focus either on improving the efficiency of the image models, like by doing model compression, distillation, proposing lighter convolutional modules, or having some sort of budget methods. And then there is also people focus also on improving the efficiency of temporal video models, like using multi-scale or combining, adjusting the 2D models to include temporal features and reuse of features or variable update rates or others. And to address the part with the labels that I mentioned, labels being very expensive to obtain, in all these kind of works, you can also think of self-supervised methods to alleviate the labeling cost. And I will now focus a bit on this part, like how can we deal with bypassing the cost of obtaining labels for videos. So this is just a quick sketch of the learning landscape that you're probably familiar with. So we have the supervised learning, which is kind of the most mature field at the moment, and then we have the unsupervised domain, where we try to learn the structure in the data without human provided labels. Then of course reinforcement learning, evolution, but I won't touch on those. And recently a topic that has become more and more popular is self-supervised learning, which sits somewhere at the boundary between supervised learning and unsupervised learning. So basically in self-supervised learning, we use large data sets, and for which we don't have labels provided by humans, but for which we can generate labels automatically. And then we define some proxy tasks using these automatically generated labels to learn a mapping from our inputs to this label space. And then we rely on transfer learning to transfer features learned in this self-supervised regime to transfer to downstream tasks. So downstream tasks that we actually care about. So for example, you can think of tracking or segmentation in videos, or action recognition, or other tasks. So you can imagine that in this kind of tasks, for example, especially like on segmentation, it's very expensive to obtain such labels. So using any kind of pre-training to have good features to start with, and then you fine-tune on these downstream tasks is very important. So lucky enough, when dealing with videos, we have lots of options for designing proxy tasks that are needed in self-supervision. Because in videos we have several modalities, and then we can have tasks within modality or across modalities. So as you can see here, in a video we have the input visual frames, but then we also have audio, and we can also have the language, like a transcript of the video, which can be obtained automatically, or maybe we have it like captions from humans. And here are some examples of works that are done in the space. So starting from the left with tasks that are defined on images, going towards the right to tasks that are defined in videos and the different modalities that we have in videos. So we have many works at the intersection of video and language, or video and audio. So yeah. And in all these different works, the most common learning loss used is contrastive losses. And I will just give some details of a work that we've published recently with my colleagues in DeepMind that is called Brave. So here the main idea is to use two different views of a video and regress one representation from the other. And this is built on top of BIAL, so building your own latents, if you're familiar with that work. So BIAL is different from contrastive losses. So in contrastive losses, you generally use positive examples and negative examples, and then you have a model that learns to distinguish between positives and negatives. However, the problem with that is that you generally need to have you have to be very careful how you build these negative examples, because if they are too easy, then they don't provide enough learning signal. If they are too hard, maybe they're noisy, and then they still hinder learning. And in general, it requires training with very large batches. So you have to show your model a large number of negatives for every training iteration, and this can be very expensive. So in BIAL, they propose this alternative method where you actually just regress. You have a two-branch network, and you regress the representation of one from the other. And BIAL was proposed for images. And here in our work, we extended the BIAL to videos. So basically, we have two views extracted from a video, one narrow view, what we call narrow view, and one broad view. And the narrow view covers less field, in less temporal field or less spatial field, but has a higher resolution. Whereas the broad view covers a larger view of the video, but at a lower resolution. And then we force each branch to predict the representation of the other branch. And then for downstream tasks, we keep the representation of the narrow view for downstream tasks. So basically, the intuition is that the narrow view has to learn the context in which that kind of action or that video segment would have appeared. So and in the same time, it might also learn to ignore details that maybe are not important. So because it has to regress this broader view that has a lower resolution. And then as broad view, we can use different modalities from video. So we can use audio, but we can also use optical flow. We can also use different augmentations on the video stream. For example, we use the random convolutions, which is an extreme form of data augmentation. So yeah, in detail, these are the losses that we use to train. So basically, in each head tries to regress the representation of the other head, and we have these two loss terms. In each term, one branch is on one branch we stop the gradients, because otherwise the learning would collapse. So yeah, and this kind of approach leads to really good performance, so state-of-the-art results on video and audio data sets. Okay, so I've covered. I tried to cover a bit the space of self-supervised learning that helps us alleviate the problem of labels, of labeling the videos. Now I will switch focus towards problems related to latency and throughput in video processing. So, and for this, as I mentioned, I will talk about depth parallel models. So the works that I've mentioned earlier that try to improve efficiency of video models, importantly, they all use a sequential execution mode over depth. So you have the data goes layer by layer into through your network, and all the layers are blocked until all the layers finish the computation for that one frame. And basically, we're saying that is not needed. And one source of inspiration, let's say, is the human brain, where So this is a nice paper from the neuroscience community asking the question, how come is the human brain so efficient? So as I mentioned earlier, the human brain consumes like 10 times less energy than one GPU, and still does so many tasks. And their answer is that the massive parallelism that is used in the brain is responsible for the high performance that we are observing. So kind of the same inspiration was used long ago already in general computer processors. Maybe you've learned, if you've done any computer engineering, you might have learned about pipelining instructions, where the idea is that you break a big instruction, you break it into smaller chunks, into smaller sub-instructions, and then you pipeline those instructions so that over time you can maximize the throughput, and you can efficiently use your hardware resources. So you assume that you have parallel hardware resources, and then you just, this is a way to make them work efficiently all in parallel. So I will dive a bit into how we can do depth parallelism at inference time and then at training time. And in both cases, the focus is to increase throughput, reduce latency, and then reduce the clock cycles as well. But I won't go much into that. And I'll just mention briefly at the end the biological plausibility aspects. So for at inference time, I'm showing here like a standard frame-by-frame model, and the horizontal axis denotes the computation time, and on the vertical we show the different layers of the network along depth. And we unroll this model over time to process the frames of a video, but we take into account that computation is actually not instantaneous. So every time a layer processes a frame, it also advances in time. And when the network finishes processing that one frame, it can only then start processing the next frame. And yeah, we're just using here some color scheme to illustrate which frame, which input frame generates some activations. So for example, blue activations come from the blue frame, and green activations from the green frame, and so on. And now this is a purely sequential operation mode. And all the modules of the network, they have to stay idle until all the other layers finish the computation. But we are saying that this is completely wasteful and unnecessary. So all these gray layers that you see here, they're just idle most of the time. So what we are proposing is to use a pipelining mechanism. So as soon as a layer finishes computation, it passes the activations to the next layer, and then it can immediately start processing the next frame. So no need to stay idle until the network finishes processing that frame. And by doing this, we are basically just rewiring this unrolled model, and this leads to a considerably increased throughput of the system. However, here the latency is still the same. The change in connectivity only improved the throughput part. So to actually deal with the latency part, we are changing the learning loss. So basically, we're forcing the network to make predictions before processing fully that frame. So basically, yeah, predicting the future. So of course now we have a low latency, and this and importantly, this becomes now is like a knob that we can turn. Like if we want faster models, then we can we decide how much we shift this the label that we have here. But in the same time, by having lower latency, we are also making the task more difficult, because then the model has to predict more into the future. And yeah, we've showed that this can learn. So even if the task can becomes more difficult, this still works. And we've shown that we can apply this kind of mechanism to various existing image models like DenseNet or Inception. And yeah, and this is like in a sketch to see how the different GPU looks when we have parallel resources available. How does this look like? So on the top you see a sequential model where every GPU just waits for its turn to come to process a frame, whereas on the bottom in our setting we have the fully parallel execution mode where all the GPUs work all the time. So this is a much better use of hardware resources. And of course, as I said, the task now becomes more difficult and we lose some in accuracy, but we can recover a good amount, a good chunk of accuracy by doing distillation. So we consider that we have around a standard video model, and then we distill from that into the depth parallel model, and that really helps learning. So yeah, maybe just to mention that the results I've shown before, they're actually obtained in an unfair way for our model, because our model is real time by design, and we are comparing it with a standard model that has high latency and which is not real time. But that was kind of the best we knew how to do when we published the paper. But there was this other paper that was published last year in ECCV, which proposes a nice framework for evaluating real-time models. So this towards streaming perception, where they actually let's say they separate the execution of the model from the evaluation. So you have this asynchronous evaluation where the model just writes whenever it finishes the execution, it just writes in a buffer. And then you have your evaluator job that just reads at regular time intervals. It just reads whatever it finds in that output buffer and evaluates against that. And in this way, you can actually, you do a fair evaluation. And they've shown actually that for models that have an offline precision of 38, which is decent, actually this drops a lot, like to 20, when you consider this fair, which is more correct evaluation mode. So I will just briefly go through how we can do training with the same kind of design principles, like to still have depth parallelism during training. And just going back to the original figure where I was showing how all the layers are blocked during execution, the exact same thing actually happens during training. So the layers are waiting for the forward pass to finish, and then they're also waiting for the backward pass to finish. Like you compute activations, and then you compute the gradients, and every layer has to wait until their turn to update its weights and so on. And again, this is we are arguing that this is unnecessary. So concurrently, colleagues from Google have observed that we can use pipelining mechanisms for training for image models, and basically they use pipelining for computations of activations and of gradients. But they require a buffer, like a large buffer, where you keep around activations for when you will need them to compute your gradients. And this is what creates this bubble here. So that is like a time where you need to stop, a time when you accumulate forward activations that you would reuse later on when you want to compute your gradients and to update your weights correctly. And we kind of take this idea to the extreme and say that actually for videos, probably we don't need to block. We don't need that kind of buffer. We don't need that bubble area. Because in videos, consecutive frames, they are very, very similar. So the question is, do we need to buffer? Like if we know that the activations of the next frame, they will be very similar to the activations of the current frame. Do I need to keep the activations of the current frame, or could I just overwrite with activations from the next frame and move on? Like to send everything, all the information, to send it forward in time. And this is exactly what we have proposed in our sideways work. So basically, here I'm showing sideways versus regular backprop. So at the top, this is exactly what we are doing. Like we are computing activations, and then when it comes to compute gradients, we take activations from later frames, so that we don't need to store activations in a buffer. So we just overwrite activations with the more recent activations and compute approximate gradients. And we've shown that this actually works very well. So like to have an image of what we are actually doing, like if we are to plot like this kind of landscape where we have on the x-axis the correctness of gradients, and then on the y-axis the speed of computing those gradients. So we could start at the very right with the Newton methods that have more correct gradients, and then going to the left to gradient descent and the stochastic gradient descent, we start getting more noisier gradients, but which are computed in a more efficient way. And our method would be there at the top with, let's say, even less, more biased gradients, but computed much faster. And actually, surprisingly, we've seen that with our training mechanism, we for smaller data sets at least, we obtain even better accuracy than the standard backprop. And the reason for this is that the noisy gradients, they act as a regularization mechanism in training. Now, sideways, as I've shown, it is a 2D model, so it's an image model. But at the very beginning, I tried to convince you that it's important to reason about temporal features, because motion is so important. So that's why we created this extension of sideways to try to take into account temporal features. And this is our recent work, Skip Sideways, which was presented just 2 months ago, or in CVPR. So basically, we are repurposing the role of skip connections to be able to extract temporal features, even though we are like in a 2D model framework. So as you already know, probably skip connections are used to create shortcuts over data paths to avoid vanishing gradients. And they were proposed like in ResNet, in residual networks. In our pipeline setting, we showed that skip connections can be used to create shortcuts over time. And this is what makes our model temporal and gives it the possibility to reason about temporal features. So if for people who are familiar with the temporal shift modules paper, for example, there we have a very similar, they have a very similar setting where you have a 2D model, 2D image model, but you want to have a temporal, the ability to extract temporal features. So basically there they shift manually activations at different time steps so that they can combine, so different layers can combine activations that originate in different frames. And yeah, as I said, they have to do this like manually to do this shift. Whereas for us in our setting on the left that you see here, because we have this this pipelining of operations and we always send all the information forward in time. When we add the skip connections, this combination of features that originate in frames from different time steps, this occurs naturally. So yeah, we don't need to do this by hand. And importantly, it doesn't require any additional buffering. So, and these are the results that we've obtained on different popular video benchmarks with our skip sideways and compared with our sideways, our previous sideways. So we can observe that the accuracy improved significantly on all the benchmarks, and especially like the kinetics benchmark, which is a large scale benchmark. And to our knowledge, this is the first work to show approximate backpropagation schemes working at large scale. So, like just a brief comparison between the models that I've shown. So we have backpropagation, gpipe work that I've mentioned from Google, and then sideways or skip sideways from our team. We could say that backprop and gpipe, they're more general in the types of inputs that they can process. So they make no assumption about the inputs. Whereas for us, for sideways and skip sideways, it is very important to deal with temporally smooth sequences, and we are saying that videos are exactly that. So we should exploit that that smoothness in time that we have in videos. And then, backpropagation based on chain rule, and gpipe and ours are similar in that they both use pipelining of operations. Backpropagations require blocking of operations, whereas gpipe has a partial blocking, and ours doesn't require any kind of blocking of operations. So, as I mentioned, as soon as a layer finishes processing a frame, it sends the activations to the next layer and can start processing a new frame immediately. Our model doesn't require buffering, whereas the others do require buffering. And our method, because it bypasses buffering, this results in using approximate gradients, whereas gpipe and backprop, they use more correct gradients. So maybe just to say very few words about the biological plausibility of, or better say implausibility of backprop. This is a figure from a paper, an Upland paper in 2016, which highlights why backprop is biologically implausible. And then there are different works that try to find more plausible training schemes. And on the left, we have the standard backprop. And as you know, as I've shown, it relies on global propagation of error signals through symmetric weights. And that is like the backward pass uses the transpose of the weights involved in the forward pass to compute weight updates. So these symmetrical weights and the blocking of computation to propagate the error from top to bottom, these are not biologically plausible. And then on the right, we see different methods that try to get rid of these symmetrical weights. So for example, in B, in feedback alignment, the author proposed to use a fixed random set of weights instead of the transpose. And then the network has to learn to use this signal to adapt its forward weights. And this works to some extent. It was shown to work. But again, as I said, these works were shown on fairly small data sets or even synthetic data sets, whereas with our approximate scheme, we have shown results at large scale. We think that sideways, for all these reasons, it is more biologically plausible. So just to mention a concurrent work, a theoretical work that is very similar in connectivity to ours, where they use diffusion equations to frame backprop, and this actually results in a more biologically plausible training scheme. So yeah, they just gave a theoretical framework, and I am actually very curious to see if we can combine their theoretical findings with our empirical results to actually have a very principled training scheme. Okay, so to conclude. So I've presented different design principles for efficient training and inference by using either self-supervised tasks or by using pipelining in operations at both training and inference time. And the main idea is to exploit the temporal smoothness of videos to speed up both training and inference. And importantly, with our proposed schemes, the latency and throughput are not dependent anymore on the depth of the network. We can increase the depth now without affecting the latency. And the important next steps are to, as I mentioned, to define a principled theoretical framework for convergence with approximate gradients. And something that would be really interesting to see is to combine the skip sideways with self-supervision to obtain a local learning rule. So I would end with my vision to how to solve vision. So maybe some of you are familiar with LeCun's cake that I'm showing here on the right at the top. So basically, he's saying that the most important part in learning relies on self-supervised learning, because this kind of task can bring the most information in the learning process. And then the icing on the cake is just is the supervised learning, and then the cherry on top is the RL. So he's making these distinctions based on how much information you can get when you train your system. And I, from my perspective, my plan is somehow very similar to what he is proposing, but I'm just looking at it from the types of skills that the resulting models can get. So I think self-supervised learning is very important and should be like the very first, like the fundamental thing, the starting point, and that this can lead to a rough model of the visual observations, and then going to self-supervised multimodal learning will help us to ground across senses. So basically to obtain common sense, obtain a model that is able to reason about its environment from the different senses that it has. So audio, vision, touch, maybe in the future we'll have language and so on. And then the very last thing, but still very important, is the part of active learning, interaction and intervention. So maybe this would be equivalent to the RL part that LeCun calls the cherry on the cake. I think this is actually more than just a cherry on top, because I think this is crucial for learning a causal perceptual model of the world. So I think that only by intervention, only by changing the state of the world, only then you can learn a causal, a fully grounded causal model of the world. So, yeah, and just to say, when I say intervention and active learning, I'm not really referring to this paper that is very often cited. Just so this was a study back in the 60s when some authors did an experiment on kittens, and they concluded that if kittens are not able to see their limbs moving, that they don't learn vision well. And it's been very cited, and it's used even today in many presentations. But just so you know, 10 years later or 15 years later, it was debunked by other researchers who showed that actually the environment was very boring for the kittens who couldn't move themselves. So because the environment was boring, they were not attracted to it. They were not drawn to. They were not paying attention to the environment. So that's why they didn't learn to see. So yeah, I thought that it's good for you to know. People don't cite the debunking experiment. They all cite the original experiment, but I think that's a wrong. That the original experiment draw the wrong conclusion. But even though, even in this case, I still think that interaction is very useful for learning. So I guess my final note on this is that as a scientist, as a researcher, you have to question. Always, you have to question everything. Don't take things for granted. Try to understand things your own way. Don't take others' understanding for granted. Try to look at things in a different way, because then you might come up with original ideas on how to improve existing methods. Okay, and I think this applies in the everyday life as well, not only in science. Okay, thank you. If there are questions, I'm not sure if we are late. Okay, if there are some questions, as Razvan said, I'm also on Slack, so I can also answer questions there.
Maybe I will step in as well, and I can read the questions for you, Viorica.
Okay, I stopped presentation now.
Okay, so the first question was how to deal with relativity in motion. For example, a person moving as versus the person who is stationary.
So I'm not sure if this is referring to like using ego motion or using external view of the person. So I guess if it's ego motion, I think that gives us already a really crucial signal, because when you have a person moving, like if you have active vision, then you have control over the camera, and then you can predict the changes that you will observe in the visual field based on the actions that you're taking. Like if I rotate my head, I can predict that I will see now this lamp instead of this screen, and so on. So using active vision actually gives you extra learning signal. But then you also have like different degrees of freedom to control. And generally, I did some work in active vision using reinforcement learning, because then you frame the process as as a decision process where you can take discrete decision where to look and when to look in the to process your input data. And I think this is also, I didn't mention this line of work, but this is very important, like to decide which data to process, because if you have limited resources, which you do generally in a real-time system, in an embedded system, you cannot afford to process all the data that you have around you, and to process it at the highest resolution possible. So then you need to choose what is most useful to process, and that is active learning, which I think it's a really great direction. And I started working on this myself with the robotics team.
Excellent, thank you. The next question is, could you please give a definition of causality? I don't quite understand why 3D convolutions would be more tricky than 2D ones. In what way are we looking at the future? Is it complication of computation during backprop? Question.
So what I mean, yeah, probably this is an abuse of terms with causality, because it's used in different ways in different fields. So by causality, I mean a model that reasons about that computes is information from the data that it's seen, so that it doesn't look into the future to make decisions for the present, because the future is not available. You can make predictions about the future, but you cannot see the ground truth. You cannot see the actual data in the future. And 3D convolutions, they have this symmetrical receptive field. So to compute one unit at time t, you have a 3D kernel, which has dimension k by k by k, and k, the first two k, let's say, are in space. So you have, like, let's say, a 5 by 5 filter, and then the last dimension is in time. And for that, you would look into the future. And these 3D convolutional models, they were designed for offline processing of videos, where you have access to the full sequence of the full video sequence. But that does not apply when you go in a real-time application where you receive frame by frame your data. You cannot use that kind of computation, right? Because at time t, you only have seen frames until time t. You cannot, you don't have access to t+1, t+2. And that's why I said that you can use masked 3D convolutions, which effectively just zero out the part of the kernel that would look into the future.
Mm-hmm. Thank you. Okay, now we're moving on to next question, which is, do you think vision can be solved by fully connectionist methods, or is it some form of symbol manipulation is necessary?
So I guess learning as opposed to symbolic methods. I do hope that learning will take us all the way. But what I think is important, and I didn't mention at all, is evolution. Because I think now we are putting a lot of pressure on one model to learn everything like starts from scratch and to learn everything like end to end. That's what we call end to end within one lifetime. You have one attempt to learn the right features. But in this we're ignoring like evolutionary approaches, where we should have populations and then we should have different generations, where you have the chance to improve. Like, okay, you took one step, you learned some tasks, you did you obtained some accuracy, but then you should be able to try different configurations in different generations to try to actually achieve a good like the best performance possible. So I do think learning. So yeah, for me, it's learning and evolution that should be combined to actually solve vision. And I think in a sense, so it's not at all the same with evolutions and populations, but the way we are reasoning now about pre-training in a self-supervised way and then going to fine-tuning on downstream tasks, this already brings this kind of idea of multiple layers in training, like on a temporal scale. But yeah, I think we need more also evolutionary approaches brought in.
Mm-hmm. Excellent, thank you. And one final question, and I remind everyone that we can take the questions to the Slack. So the final question would be, how would you deal with non-IAD data, since SGD does not work in that case? So I think that is meaning specifically to video, probably.
Right. So I think in Sideways, we are trying to exploit the fact that the data is correlated, and we are relying on that to like we are trying to exploit that, to exploit the redundancy and the correlation that we have in videos. So we are still computing gradients for a sequence, and we are averaging. So one sample for us is still one video sequence, and then we have different samples. We are still in the SGD kind of setting where we have different video sequences, like we train over a batch, and those are IID. But the way we compute the gradients for one sample, that is there that we are exploiting the correlation in the video. But across videos, those should be IID.
Excellent. Thank you. And I believe we should be wrapping up the Q&A session at this point. Thank you so much, Viorica.
Okay,
let's take the rest of the questions to the Slack. And now we will be moving to short quiz. Excellent. So everyone, please use your real name and please do record the screenshot of you winning the quiz or earning a high spot. It's going to be 3 questions once again, and then we are going to go on to a break. So if everyone is ready, we can starting the quiz. Yeah. And the quiz, please join the quiz with your real name. And we see people are joining. Excellent. Please keep joining. Excellent, excellent. Get excited about those books. It's 3 books that you can win. It's either Bishop's Pattern Recognition or Causal Inference book or Sutton's Reinforcement Learning. And we have 55 people already. Let's give it just a few more seconds. Please get excited and join the quiz. It's up to 60 people. Excellent. Just a few more seconds. And okay, I think we should go ahead and slowly start to get started. And now we still have people joining. Okay. And I think it's time to start. What is the naive Bayes algorithm called? Naive. So just one right answer. And you got 3 more seconds. And correct. Majority people have answered. All right, now we are moving on to the next question, probably. Okay, you see the leaderboard. Which of these is not a type of penalized regression? So you got 6 seconds to answer. All right, an interesting distribution within the answers. And we're moving on to the next. And the final question, which one of these statements about the R squared is incorrect? We've got 5 seconds left to answer the question. Interesting. And at this point, we are wrapping up the quiz. As I've mentioned, the people will be awarded for their participation in the quiz tomorrow. And now we are going on to the short break, and then we'll have the next speaker. Okay, we are back after the break. Glad to see everyone back. Now we have our next speaker lined up. Donatas from Biomatter Designs will talk to us about generative models, and I will pass the microphone straight away now. So here you go.
Hello, everyone. So I'm pretty pleased to be here and having this opportunity to talk about the work we're doing at Biomatter Designs. So before we get into this workshop, just quick introductions. So I'm CTO of Biomatter Designs, a young startup. So my background is in computer science. I'm computer science by training, and then I worked as application developer, data scientist, machine learning engineer in companies like JP Morgan Chase and IBM, until I, with few colleagues of mine, started this startup. And what we do in our startup is that we focus on developing new tools, computational methods to improve protein engineering process. Currently, the process is heavily dependent on the experimental work. Our goal is to move that heavy load of work onto computers using AI methods, machine learning methods, and making this is way faster, way cheaper, and way more controllable. And our research is mainly focusing on applying the things which we know from computer science research, which works on other data sources, and applying them on protein engineering and just changing them so they still work. And this workshop will demonstrate that not everything can be applied straight out of the box. You have to make some changes and to make them work as intended. Yeah, so going back to this presentation or session, this will be slightly different session from what you heard before. This is very practical session, so the only thing I have here is the notebook, which you will get access to, and you will be able to run all the things you see here on the screen yourself and play around. I do assume some knowledge, so I'll skip some basic stuff. So I assume you know TensorFlow library, you know some basics about neural networks, and you have some understanding what generative adversarial networks are. But if you don't have them, these prerequisites, feel free to listen and then just later on fill the gaps where needed. Yeah, so as the title says, I'll be talking about generative modeling, more specifically about generative adversarial networks. And the reason why we were interested in that method is its ability to generate high quality samples. And on the screen, this is a picture generated by StyleGAN to one of the implementations of GANs. And it looks remarkably realistic. And it looks like picture of me, but it's actually not. It's not my picture. And the GAN or the generator never saw a picture of me. I'm pretty sure of that. So this ability to create this picture out of random noise is something we would like to apply in protein engineering. So just to give a brief background about why we're interested in protein engineering and what it does for us. So the easiest thing to think about proteins for me is to think about them as being a very small nanorobots, which are programmable. So you can make them to do some simple tasks, and nature uses that to do all sorts of things. For example, this is sorry. So this is this was a video of protein which does the transportation in every human being. So it just moves things around. And this is a sort of one example of protein in human body, and we have loads of them, and they do perform different functions. So that's very useful to do all sorts of things, starting from drugs, going to industry, making chemical compounds. But the problem with this is that we don't really understand how this is actually, how we can program that. We don't know this code yet, and we don't fully understand. We just know some concepts. So that's why generative adversarial networks seems to be a good fit. And if we just try to compare images and proteins, we'll see that there are some similarities. So first of all, if you think about images, they are made of pixel values. And if you try to randomly arrange pixel values, you will get a noisy picture of nothing. So it wouldn't make any sense. The same applies for proteins. They are made of 20 discrete or different amino acids, and you can chain them in the way you want, in theory, and only small fraction of those will result in something meaningful. So you can't do that randomly, and even you can't use the brute force to check all the combinations, because the number of combinations is way larger than we can process. So that's one thing. Another thing is that similarly, the same as with images, we really don't know what is a good protein. The same way we can't describe mathematically what is good picture, which picture looks realistic and which is not. There is no easy way to measure that. The same is with proteins. We really don't understand that well. All the things that we could say without going without testing experimentally. As I mentioned, the experimental work is quite expensive. So we would like to have ability to create high quality example of proteins, which follows the rules of nature, which we don't know, but we want to infer that from the data we have. And we have quite a number of sequences which we know works, and we can use that to train the neural networks. So you have here just a summary table. And one thing which is important to mention here, that while there are similarities between proteins and images, there is one big difference, and that is that proteins are built up of categorical variables. So we have 20 amino acids, whereas images is you can think of continuous values or continuous values of pixel density. So it's ranging between 0 to 255, but well, we normalize between 1 and between 0 and 1, but it's a continuous value, whereas for proteins you have to choose 1 out of 20, and that is a sort of problems for GANs. And I will demonstrate that is actually taking the GANs which works on images doesn't necessarily mean that it will work on different data set. And in this case, on protein engineering or generation. So if you are interested, you can read the paper we published in Nature Machine Intelligence, more about this. There is a link. So to get a better understanding what the protein is, this is a 3D structure of the protein. So we have a sequence here, which is a primary structure as amino acids. Each letter is amino acid. but in fact, in real world, that sequence of amino acids falls into 3D structure, which is a cartoon representation of that 3D structure. And that's something, this is something, that's the 3D structure of that protein. So that's how our inputs looks like. And for this workshop, I'll just try to show you a toy example of GANs, which is capable of generating proteins. So in order to do that, we will just need to set up our environment first. So it's nothing fancy going on here, just installing some dependencies, fetching the data, which I prepared earlier, some imports and helper methods to make the code cleaner and easier to modify. Then nothing to worry about here. So the next bit and the next important bit for any machine learning problem is the data. So for this, we will use the cytidine deaminase protein, the one just a very small protein, which is essential for DNA and RNA degradation in organisms. And we want to create different variants of those proteins, which we can't find in nature, but they still perform some function, the same function, but because they're different in amino acid sequence, they will have different properties, and then we can try to look for something interesting. So yeah, so I'll use my data set from TensorFlow. So it's just a standard piece of code. You just read the file with the sequences, batch that, and just as a good practice, I'll print what I get. And you see this again, a sequence of amino acids. It's important to notice that there are a variety of amino acids used. So in reality, nature uses pretty much all of them to create functional protein. So that's something we should keep in mind when looking at the results. Other than that, it's difficult to say anything else about this. So just we trust that it's a good experimental data, and yeah. So we have a data ready. We'll move on building the baseline model. And for this, we'll start with discriminator and generator. I have two main components for GANs. So in terms of architecture of those neural networks, I try to keep them as simple as possible and as standard as possible as well. So this is just adopted from some online tutorials without making any significant changes. The only major difference is that I changed 2D convolutions to 1D convolutions. So just because we are now dealing with 1D object, a sequence of amino acid. I think it's important to mention that these architectures can be improved and tailored for more specific, to be more specific and more even better for protein engineering or any kind of problem, which is where the input is discrete. But for the sake of this workshop, I leave this out of the scope and we'll stick with what we got here. And yeah, so this is the architecture. You see, it's not huge. It's roughly 500,000 parameters for the discriminator, and same applies for generator. So yeah, we will use that to build our GAN. I guess, well, I see one question which I can answer right now. In terms of if proteins are more similar to text than images, the answer to that is probably yes and no at the same time. Yes, in terms of that they are sequences of discrete things. No, in terms of vocabulary size, because you have so many different words, whereas for proteins, it's only 20 of them. So if we want to apply GANs for text generations, that would be an issue. The vocabulary size would be an issue, whereas in this case, it's still doable and we can make GANs work. So yeah, moving on. So we have the discriminator and generator created. So we need combine those two things, and we'll use a Keras API for that. We'll extend the Keras model class. And again, this is a modified version of online tutorials. We'll base our GAN on Wasserstein GAN version. We'll skip the fact, well, the part where discriminator is trained multiple times compared to the generator. From my experiments, I didn't find any improvements or any significant improvements when training this discriminator more times. There might be somewhat specific to the problem as well, or I would say there were other problems more significant that this training multiple times the discriminator didn't solve. So yeah, so we have this class extended, and we just take discriminator and generator as input. We do create optimizers for each of the neural network. We will track the loss. We'll pass the loss as well, and then we have a step counter, which we'll use later. Yeah, I mentioned in metrics, and then this is a sort of boilerplate code. We'll have a method for generating sequences. So we'll take a random noise, feed that through the generator, and that just gets returns the generated sequences. Then we have two methods, one for training discriminator and one for training generator. So this is very standard code. We just use as it is. Pretty much we apply the gradients, so we just get the those two neural networks optimized, and then we override the training steps to make those optimizations of generator and discriminator both in one step. So this is where it happens. So we have we training the discriminator and generator in one training step. We updated our metrics, which we will follow through, and then another thing which is going here is that we do one hot encode our input, which is yeah, so we just take IDs of each amino acid and then convert that to one hot encoded version. So yeah, that's our model. So the only missing piece is the loss. I'll took the loss from this link of Keras examples. So is standard loss where we have discriminator and generator having opposite goals. So I think we have all the components we need to run our GAN. So this is the baseline. We'll see how it goes. We'll run it for 25 epochs. I just repeated the data set 5 times just to make the output cleaner, but in fact it's just 25 epochs. And one last thing that we'll use tool called BLAST to evaluate our sequences. It's not really important to understand how this works, but the way we will use this, that we want to have as many hits as we can, and we try to get as high scores as possible. So the higher the score, the better. The more hits, the better. So that's what we sort of aim for. And I just put a note here just to keep in mind that the generator never saw training data set, not to mention validation sequences, which will be used for BLAST as a database. So it's not even used in training. So yeah. Okay, so we can run this. So it's because it's a small model, it runs pretty fast. So we ran for 25 epochs. This is these two lines after each 5 epochs. This is generated sequences from the generator. And even if you don't know a lot about protein engineering, you see that this doesn't look right. They are the same. They're not using all the amino acids. It's just something off. And that's definitely a first thing to notice, that, and it's pretty safe to say that this is not going to work. It's not going to do anything good. If you try to put this sequence in the lab and try to test it, you won't get any results. Another thing which becomes obvious right now is that loss is all over the place. It's going from big numbers to small numbers. It's jumping, it's not stable. And GANs are really hard to train because of stability issues, and this is really not great. But we can try to mitigate this issue. So the first thing we'll try is a non-saturating loss, and that's the loss which was proposed by original paper of GANs by Ian Goodfellow, and that's the formula. But the main idea is just you don't go beyond 0, and if we will apply the soft plus operation, but it is the easiest thing to, well, the way I think about this operation is just ReLU, which is smooth. So it just, if it goes beyond 0, that's just 0. Other than that, it's just a value of what we got. So we apply that to generator loss as well. And again, the same code, we'll run it. We'll run that for 25 epochs and see what we get. And as you can see here, the loss is behaving better. Sequences also having more unique amino acids, but we're not getting any hits as not yet. And it seems like actually kind of entering motor collapse as such. So the first and second sequence is, well, very, very similar. So that's not really what we want. And it doesn't seem to actually going to converge anytime soon to something good. And one of the things when we did this work, we found out that there is a family of losses for GANs which actually have local convergence, and this is work by this guy and his team. They did analysis, theoretical analysis of GANs and how they converge, and their finding is that the GANs with zero-centered gradient penalties do converge, and that's the one nice example where theoretical work is actually working in practice as intended without any hiccups. So what we're gonna do, we just apply this gradient penalty, and it's called R2. So this is the formula, and this is simply applying on the data, on the input data. And implementation will be done with gradient tape. So what we do here is we just extend our discriminator, train discriminator method, and we just have another gradient tape, which actually calculates gradients with respect with real sequences. So we just watch that and then ask TensorFlow to provide the gradients for that. And this becomes a term to the loss here. We just append this number to the loss. And this was, during our research, a very significant boost in terms of convergence speed, whereas other methods that didn't seem to converge or did it very slowly. So yeah, so that it was something we noticed. There is a multiplier here, is a hyperparameter, which it's then divided by 2 usually because of 2 here. You can play around with this one. If you don't change it significantly, you won't probably notice any difference. If you go with completely like a very huge or a very low number, you probably see you will see the impact. But this does a really good job. And the same, the rest of the code is the same. Yeah, so we added this, and we'll try to train the discriminator again, same 25 epochs. And this time, this is looking better. We actually getting some hits, some scores, but that is not consistent. And we can do better than that. So one thing that we ignored up till now is that we try to generate one-hot encoded sequences. And if we just take some generated sequences and try to print some positions in those sequences, we'll see that it doesn't look like one-hot encoded at all. And that's the thing which Scan has to learn how to do it, but it's really difficult to achieve this by just using non-linearities and matrix multiplication. And what a good illustration what it does is that if we take the same sequences which were generated right here, and we'll try to get the score from discriminator, we get this number. But if we just apply argmax operation and then do the one-hot encoding, which effectively just converts these numbers in one to become one-hot encoding, the score of discriminators changes dramatically. And we would like to have the one-hot encoded version of these sequences, but we can't use argmax operation as it doesn't allow gradients to go through. So you won't be able to train end to end. So you need to find another way to do it. And luckily, again, there has been some research done on this, and this is a topic as well, which is of interest in reinforcement learning, I believe. So we can utilize the Gumbel softmax distribution to approximate one-hot encoded distribution. For us, TensorFlow probability library has done the work. So they implemented this approximation, and it's just relaxed one-hot and categorical class method, maybe class. which allows you to do that. So, and this is the example how you can use it. So we have logits which are coming from generator. Let's imagine that is pretty much these numbers, but just simplified version. And let's assume these are probabilities of amino acid 1, 2, and 3. And what we want to do is to convert that to one hot encoded. So we'll use this relaxed one hot categorical with these logits, and then we'll see what we get. And in fact, it looks like one hot encoded version of the same thing. So yeah, so that's very useful, and it's very good that TensorFlow has this implemented. We don't need to worry about this part. So we can add this to our GAN. So we just extend the previous version and override the generate sequence method. And what happens here is pretty much we generate the sequences and then use these generated sequences as logits for relaxed one hot categorical, which actually spits out something which is more like one hot encoded version of the same thing. One hyperparameter is the temperature. Generally, you want to reduce this temperature as the training progresses. That's why we calculated steps. So we have a schedule, and we decrease the temperature as we train our GANs. Okay, so we have this, and that's the version we want to train. The loss is still the same as before. We haven't changed anything. So we ran this for 5 epochs, and straight away we can see that we starting getting some hits, and nothing good though at the beginning, but later on we have way more hits and the score is increasing, which means that GANs, this version of GANs is actually capable of learning this, how to create proteins and follow some rules from nature to make them look realistic, so that the discriminator can distinguish with them, between them easily. And then if we look at the generated sequences and at position 45, we'll see that this looks like a one hot encoded, and that's a good sign. Again, we can do the same thing where we take generated sequences, feed that through the discriminator, I get some score, and we apply on the same sequences the argmax operation and one hot encoding, and get a pretty much the same score, which means that the sequences which are generated by generator looks way more like the ones from the data set, and now discriminator can't rely on looking at these numbers and seeing that they are not one hot encoded. That means it's fake is generated. Now it has to pay attention to other things, other components of the sequence, which says whether this sequence is real or not. And the goal, in ideal world, what we want is just the discriminator to be able to learn laws of nature and be able to use them to create something new. So one thing which I done with this final version, so I took one of the generated sequences and tried to predict the 3D structure of the sequence. So this is the sequence I used, and what I use for prediction, structure prediction, is AlphaFold 2, a AI-based tool developed by DeepMind, and AlphaFold actually requires probably a separate session on its own. It's a incredibly incredible breakthrough, to be honest, in synthetic biology, where AlphaFold does what wasn't possible to do previously. It gets the accuracy of protein structure prediction close to the experimental one, and this is very much down to the fact that we now have deep learning models and not enough data to train those, and we don't really still understand the folding process, how we go from sequence of amino acid into 3D structure completely, but now we have a tool which can approximate this pretty accurately. So I use this AlphaFold to get the structure, and then I align this with the experimental structure from PDB database. So the green one is the generated one, and cyan is the experimentally determined structure. And as you can see, they overlap a lot, which is a good indication that the function of the protein is retained, so it's not impaired. And this is a very nice ability, because now we should be able to create more variants, which, okay, I'll go one step back. These sequences, in terms of sequences, they are only 47% similar. So this is not identical sequences. So we have a very different sequences, and they result in the same structure, and that's a good thing in terms of that we learn how to make or to create proteins which fold in the same structure, and that's just a small but significant step towards cracking the protein language, if you wish. We start, at least we have ability now to do something about the sequences, and we know what we can expect out of that. And having this ability and having this same structure means that we can do things like searching for different properties. So either it would be more stable or more active or more expressible. So yeah, and that could be useful for various purposes. So yeah, that's pretty much the end of this workshop. I talked a lot about protein engineering and protein generation, but the sort of underlying aim of this workshop was to show that you can apply GANs to different type of data, which is not images, and you can try to produce some high quality example for your data set. However, it's not very trivial to do in most of the cases, especially if your data is quite different from what the your data is different from what GANs are used to, and that means you might need to do some changes, and you might need to kind of do some research work to make them work. But I hope this serves as a good starting point and a source of ideas where and what to look for to be able to make those adjustments and to create something that works for your needs. Yeah, as I said, this notebook should be accessible to everyone. I think I saw Linus adding the link, so you can play around and find something interesting, and it could be optimized further. Yeah, so I think that concludes this notebook. We can move on questions which I didn't answer during the presentation. So yeah, I see one question here. Let me read it. So the function of protein relies on 3D structure. Wouldn't it make sense to try to calculate 3D structure that would be wanted, that would do the wanted function, and then try to work back to a sequence of amino acid that could build the determined structure? Yes. Well, it's a possible way of doing it, and there are methods and developed deep learning models which solves this problem. However, now what happens is that the 3D structure doesn't have very good resolution. And if you take two relatively similar sequences, the 3D structure will be the same. So what you get is the same input and probably 1,000 different sequences, which would give you the same structure. So what happens in practice, the people who try this, they do globally, so they do different structures and then just assign one of the sequences. But it doesn't seem to be working very well. There is no much experimental evidence that could be done very accurately, but it's definitely a way of doing it. Another one, how does generating structures like proteins, molecules via GANs compares to generating same structures using reinforcement learning? Which approach you think is better? So from what I read in papers, I saw only one example where reinforcement was used to generate protein sequences, and I don't recall that they did that they validated it experimentally. So what we did in our paper, we developed this protein GAN, as we call it, a version of GAN which generates protein sequence, and we went to the lab to do the experimental testing. Without this, it's difficult to say how well this approach works. Now, in terms of which method is better, I really don't have the answer, because there are other ways of generating sequences as well. We can use something like the same approach which is used in natural language processing. They use big transformer to predict next amino acid in autoregressive fashion. That also works. Reinforcement learning would also work, but there are no hard large-scale studies to compare them. And yeah, that's pretty much what I can say about this. I think they are valid, and we need a bit more research to get to the bottom which works better. Again, another poor thing is that each of the approach has some different properties you can explore, and with GANs you have a latent space you can navigate through. So you can take a point, you can test that experimentally, and then move to one direction and test that experimentally as well. And if you see that this direction some property changes, you can actually then go further and control some properties, which is nice. Whereas I don't know how you would do that within reinforcement learning. So there are pros and cons here. Nothing concrete. yeah, why GAN and not variational autoencoder? It's a good question. Again, after we released our paper, someone did similar thing with the variational autoencoder. And it works, and there's sort of no reason why it shouldn't. The reason why we went for GANs is its ability to create high quality images. Because if you think about proteins, even one incorrect amino acid can make protein inactive or do something very badly to it. And you want your method to be as high resolution as possible. And if you compare variational encoders and GANs at the time, there was a clear winner in terms of image quality. So we went for the GANs for that reason. Yeah, but variational autoencoder works. The paper I talked about, they did some experimental testing and they got some proteins working, but it's not directly comparable because they use different protein, which was smaller. So it's hard to compare. I guess, yeah, I don't see any other questions. So yeah.
I think we're out of questions by this point. There was only a question if there are where can the people find the collab notebook, and it has been answered in the Slido, and we've also posted it on the Slack chat, on the Slack of the event. So yeah, I guess we can start wrapping up and do the quiz a bit earlier. So thank you, Donatas, very much for your presentation and the workshop. Really appreciate that. And as mentioned before, you can probably find Donatas on Slack if he's already there. And the link to the collab notebook is available on Slack as well on the general channel. So thanks a lot, Donatas.
Thank you very much for having me.
All right. So now we are going to proceed to the final part of the quiz for today, which is going to be a third, again, 3 questions, since now instead you have 15 seconds, so a bit more than you had before. So we see people are joining. Keep it up, people, keep joining. It's an opportunity to win 3 books on pattern recognition and machine learning from Bishop, on reinforcement learning by Sutton, and a book on causal inference. 3 quite exciting topics that have a lot of things overlapping or that can reinforce one another. And we do want to encourage people to learn these topics. So that's why they're given out for free if you participate in the quiz and win. So 46 people, let's give it a few more seconds. We can give it more time since we're running a bit in front of our schedule and we'll have a longer break. So let's wait till more people join. Right, you can also share links with your friends if they would like to join late minute. Because next we will also have Brady to give a talk about causal inference, and then Z from Google Brain to talk about Bayesian optimization. So feel free to share the links to invite your friends to participate and watch the stream. All right, so we are up to 54 people. We are giving it 10 more seconds and then we'll start the quiz. Just waiting a little longer. Let's get it up to 70 people. Let's see if we get it up to 70 people. All right, 56 people, 57, excellent. Come on, just 3 books, 3 questions, and you have an opportunity to win a book. Very exciting book. 58, and give me 59. 59, excellent. I feel like I'm on an auction. 61, excellent, excellent. Where the stakes are getting larger and higher. Very exciting. And can we get up to 70? Can we get up to 70? Note that now you have 15 seconds for questions, way longer than before. So way much time to think about the questions and the answers. All right, I think we're reaching we're converging like a stochastic gradient descent to the local optimum. And we'll start the quiz shortly in 10 seconds. Okay, we're almost getting to the goal of 70. We just need 4 people. Can we get 4 people? 4 people 1, 4 people 2, 4 people 3, 4 people 5, 4 people 6. No, we got 1 more person, 67. Okay, just 3 more people. Come on, almost there. 68. Okay, we are reaching our goal. 69 and 1 more person. 70. Excellent. We start the quiz right now. Thank you, everyone. Let's start the quiz. Okay, so the first question is predicting the number of years of education that a person has received is a classification problem, a regression problem, a clustering problem, none of the above. You have 6 seconds left to guess. All right, first question is done. We see it's a regression problem. Okay, now moving on to the next. Next question is going to be, which of these statements about the gradient descent is incorrect? And you have 10 seconds to answer. So notice its statements can be multiple. 3 more seconds. And second question is over. You're out of time. Excellent. Just 1 final question for today in the quiz, and then we'll have a short break with a presentation from Brady on causal inference. Okay, next question. Which of these statements describe a statistically significant result? 9 seconds left. Okay, final attempt to answer the question. 70 lucky people. All right, excellent. So thank you all for participating in the quiz. This is the last quiz for today, but stick around because we have 2 more presentations for today. And now we are moving on to the break, and we will get back in 8 minutes, I believe.
Welcome back. I hope that you enjoyed the break. Our next speaker is Brady Neal. He's a PhD student in causal inference and machine learning at Mille, Quebec AI Institute. And today he's going to talk about introduction to causal inference. It's an increasingly important area of research in machine learning and data science, and I'm really excited to have Brady here today. So Brady, the floor is yours.
Hi, everyone. So this talk I'll be giving today is on a brief introduction to causal inference. There's a whole course I give titled Introduction to Causal Inference that you can go to after this talk if you want to at causalcourse.com. But this talk is just meant to give you some motivation and intuition for kind of the beginning of causal inference. It's like a high level of the first few weeks of the course. So you're not meant to get a complete understanding. If you want a like more in-depth understanding, that would be over a few lectures in the first weeks of the course. And then connections to machine learning, like out of distribution generalization, those come later in that course. So you can see the course and the book associated with it at causalcourse.com. This is like the first talk in the course that's meant to help motivate things. All right. So what is causal inference? We'll start with, and it's basically just inferring the effects of any treatment, policy, or intervention. So as an example, say you have a treatment and you want to measure how effective it is at treating a disease, or you have a policy to try to reduce emissions. You might be interested in the causal effect of that policy or different policies. And you could say you want to know the effects of social media on mental health. Just generally, anytime you have some X that you think might cause changes in a Y, causal inference is about measuring how Y changes in response to changes in X. So this talk will have 4 parts, and I'll pause for questions at the end of each part. So feel free to ask questions, and I'll be happy to take those at the end of each part. The first part is meant to just kind of motivate why causality is important. So basically, we'll see that for a key decision, causality is important for making that decision properly. And then the second part, we'll see, okay, correlation does not imply causation. You might have heard this before. Maybe I'll give you a bit more on that you haven't seen before. And then if correlation doesn't imply causation, and we're interested in causation, then what does imply causation? That would be the third part. And the final part, we'll see causation in observational studies. So observational studies are just when you observe some data. You're not running an experiment, but you find some data and you're trying to infer some causal effect using that data. So it's a very common use case for causal inference. All right. So with that, let's get into the first section, this motivating example. We will look at a purely hypothetical example, COVID-27. Say you have this new disease, and there's 2 treatments out for the disease, treatment A and treatment B. And let's say that it's your job to choose the treatment for your country. So it's kind of an important decision. And here I'll denote A with 0 and B with 1 in the coming slides. And let's say that you also have data not just on treatments that people have taken in the past. So these treatments are out there, and you have data on the treatments that people are taking, and you have data on the condition they have at the time of treatment. So if they have a more mild or severe condition. And then you have data on their outcomes, so if they live or die. All of these things will be binary variables just to make the example simpler. All right. So say that 16% of people who take treatment A die, and 19% of people who take treatment B die. in this case, it kind of looks like maybe treatment A is better than treatment B, but let's say that we were to zoom in and also look at their condition. So if we stratify the groups based on mild condition and severe condition, then we see that actually in the mild group, a lower proportion of people who take treatment B die. So only 15% die who take treatment B and 15% who take treatment A. And it's the same in the severe group. A lower proportion of people die who take treatment B. And so these numbers I have here, basically the denominator is just the total number of people who take who fall into that group, take treatment A and have mild condition, and then the numerator is the number of people who die. Okay, so this is an example of Simpson's paradox that you might have heard of before, just to illustrate that this is that the calculations are right here. Then I'm just showing the calculation, and and so for this first line, it's just the denominator comes from the number of people who take treatment A, so that's 1400 plus 100. That's what these denominators are, and the numerators are just the relevant conditions, and that multiplied by their mortality numbers for people with that condition. That's how I get this 16% here, and then same for treatment B. Okay, so this is one example of Simpson's paradox, but kind of the key thing that I want you to focus on here is that in this total column, we have that treatment A is the lower mortality rate, but then in the mild and severe column, so if we segment people based on their condition, then treatment B is the lower mortality rate. So, you have to choose which treatment should you choose. Is it treatment A or is it treatment B? And the spoiler here is that the treatment that you should choose, it depends on the causal structure of your problem. So in order to decide which treatment to choose, you have to know the causal structure of your problem. Okay, so I'll go into two scenarios. One where treatment B is the better one, and one where treatment A is the better one. So scenario one, where treatment B is the treatment you should choose. Here I just have the table from the last slide. In this scenario, basically it's where your data is generated in such a way where T is generated from the condition and not the other way around. So basically, C is a cause of T, T is not a cause of C, where C is the condition and T is treatment here. And then in the other scenario, it'll be flipped. Just to give you a bit of specifics about how this might work in this example, let's say that doctors are prescribing treatments based on the condition that they see people in. So here, treatment B is a more scarce treatment. So one thing I forgot to mention is just that fewer people are getting treatment B. So only 550 people get treatment B, whereas 1,500 people get treatment A. But so the doctor sees someone come in with a mild condition, and then they say, okay, they have a mild condition, so we'll give them less scarce treatment. Most people have mild condition, and so they give them treatment A most of the time. And then if they see someone that has a more severe condition, they might be more willing to give them the more scarce treatment, treatment B. Okay, so their condition here at the top is a cause of the treatment that they're given through this. The doctor is the mechanism that's allowing that. Okay, so in this kind of scenario, where the condition is a cause of treatment, and any other scenario you could imagine where a condition is a cause of treatment, you actually want to take treatment B. So you want to look at these numbers, the 10% and 20%, and those are the relevant numbers, not the 16% and 19% over here. So I'll get into why that's the case a bit more later in the talk, but just the portion of this talk is just to illustrate that causal structure is important. So, okay, just to recap, in scenario 1, treatment B is the better one. And then in this second scenario that I'll look at, treatment A is the treatment that you should choose. So this scenario, all that's changed in this causal graph, so it's just saying what variables are causing other variables. In this scenario, T, the treatment, is a cause of the condition. That's the only thing that's changed. They're still both causes of the outcome, whether the person lives or dies. Okay, so some details for how this could work in this example is, say that you come into the office to be prescribed treatment, and let's say that because treatment B is more scarce, you have to wait a longer time, and your condition can worsen while you're waiting for treatment B. So basically, because treatment B is more scarce, it makes you wait longer, so your condition can get worse while you're waiting. So treatment here is at the time that you take the treatment. And then if you were to get treatment A, it's a less scarce treatment. It's abundantly available. So if you come in with mild condition, you'll still have your mild condition by the time you actually take the treatment. So in this scenario, where this is the general causal graph you need for this scenario, but this is one example in our setting, then you would actually prefer treatment A, not treatment B. So the key thing here is that causal structure, this causal graph, matters for which treatment you would want to take in this important decision. And that's the end of this motivating example section. So any questions about this?
Yeah, so I'm not seeing any questions so far. So maybe we can give people like a minute to write down the questions. And also, I should mention that Brady is taking questions after every section so that he can answer them in a more timely manner. So please go ahead, take this opportunity to ask questions about this motivating example. I see we already have a question, yes. The first question is, not sure I understood the scenario with treatment A. How treatment can cause condition? Should I treat the scenario as only theoretical?
So the condition here is I should say, the condition you have at the time that you take the treatment. So say you were to come into the office with a mild condition, but then the condition that's being logged in the data isn't that condition at the time you come into the office, but the time that you actually take the treatment. So you come into the office and then you get prescribed treatment B, but you have to wait to actually get treatment B because it's a more scarce treatment. So while you're waiting, your condition worsens to severe. So the fact that you were prescribed treatment B has led you to have a severe condition. Whereas if you have treatment A, you might have stayed at a mild condition.
All right, we have one more question. In many cases, the actual graph is not known. How would you know that you have chosen the correct scenario?
So this is a more advanced topic, but there's ways you can try to infer the graph, which I won't cover in this talk, but it's covered in the course and book. And even when you can't infer the graph completely, you only get a partial graph. Say you don't get all the directions of the edges. There's kind of a frontier of research right now where they're trying to do causal inference in that setting, where they don't know all of the graph, but they know parts of the graph. And yeah, so I would look at some of that frontier research, but we won't see it here.
I think let's do one more, the last question. if that's okay with you, Pedro. Sorry, Brady.
Yeah.
Pedro is asking a question. In which sense the causal inference compares traditional correlation calculation? Yeah, I'm going to repeat the question. In which sense the causal inference compares, I guess, to traditional correlation calculations?
So if you just look at the kind of correlation or association between the treatment and the outcome, so T and Y, that's kind of like what this total column is. So let's see back here. So expected value of Y given T is a kind of correlation or association. That's what this total column is. And then when you stratify based on mild and severe, you're throwing in this variable that you're controlling for, C. So it's a more like fancy thing that when people say they're controlling for something, that's what it looks like. They're throwing it behind a conditioning bar here. And we'll see a bit more about this later in the talk. But this total column is kind of the naive correlation equals causation thing.
Yeah, thanks. Okay. That was the last question for this part. Let's move to the second part. So to recap, the main thing from that last part was just that causal structure is important for decisions, and the last decision was an important decision. In this part, we'll see some details about correlation does not imply causation. So you might have heard this before in a statistics class if you've taken those. If you haven't heard this before, that's fine. I'm just going to give you a quick recap of what it is. So say that you notice that people who sleep with shoes on often wake up with a headache. So it seems that sleeping with shoes on and waking up with a headache are strongly correlated. Maybe you could think that you shouldn't sleep with shoes on because you'll wake up with a headache, and that it's causal, but it also might not be causal. It could just be that people who sleep with shoes on are sleeping with shoes on because they drank the night before, and then they're also waking up with a headache because they drank the night before, drank alcohol. And so in this sense, there's a common cause, drinking the night before, that's causing the two to be associated. So you're seeing this association between the two, or correlation between the two, because there's this common cause that's causing both of them. So there's two ways to think about, well, at least two. Think about why the fact that they're associated doesn't mean that that it's a causal relationship. So one is that people who sleep with shoes on, shoe sleepers, they differ from non-shoe sleepers in a key way, and that key way has to do with this confounder. So the shoe sleepers are going to bed drunk, say, and the non-shoe sleepers are going to bed not drunk. So these two groups of people, they differ in a key way. Another way to look about it is this more graphical way that I have here in this graphic, where it's just that there's a confounder. So something that's causing both of them. And that confounder kind of allows, you can think of association flowing from the going to bed with shoes on to headache along this path through this confounder. All right. So really what you're interested in is causal association. So there is not an arrow there in this case, but that's what causal inference is trying to detect, is this arrow directly from the treatment, in this case, sleeping with shoes on, to the outcome, waking up with a headache. And you can think of total association that you measure. So that's if you were to just look at, the expected value of Y given T, or, the correlation between Y and T, you can think of that as a mixture of causal association, which is this blue line, and confounding association, the red line in this picture. And the word association just means statistical dependence.
depending on who you talk to, correlation, they might say correlation is technically, it's a linear form of statistical dependence, but colloquially, people often use correlation synonymously with association. So I'll be using the word association more, I think, because it's less ambiguous. All right, so that's how you can have, that's an illustration of why correlation does not imply causation. But one kind of tangent here is that we, as humans, we use correlation equals causation all the time. It's a cognitive bias. So say in this example, rather than having shoe sleeping as the treatment here, we just have some star. So just whatever you think might cause a headache, and then a confounder of that star and headache. So we can generate this star like in our heads when we're trying to explain our headache via another cognitive bias known as the availability heuristic. So it's just whatever is most available in our head, whatever happens to occur to us in the moment. The bias there is that stuff that is available in our head is important. Like we should think of that as maybe relevant for the thing we're thinking about, the headache in this case. And so say you have a headache and you're trying to explain why. Like, why do I have this headache? You might come up with some star to explain your headache via the availability heuristic, or motivated reasoning is another one. So say that I don't like spending time with my in-laws, my parents-in-law, say, then I might say, oh, okay, well, I noticed that I have headaches whenever I hang out with my parents-in-law, so I'm trying to give a reason for why not to spend time with my parents-in-law. And then, so we could say that this star explains the headache via correlation equals causation cognitive bias. So just noticing that the two are related. Whenever I hang out with my parents-in-law, I get a headache. So it must be that hanging out with them is causing my headache. Okay, so this is just a slide about cognitive biases that we're probably making the correlation equals causation cognitive bias all over the place. Even people like me who study this topic. And here's an example. So we have basically in red, we have the number of people who are drowned by falling into a pool each year. And then in black, we have the number of films that Nicolas Cage appears in. And the x-axis is time here. So this is a fun one. I guess maybe Nicolas Cage is driving people to drown themselves. And if you want to see more of these, they're at this website. They have all these spurious correlations. Okay. So that's the kind of the end of the correlation does not imply causation section. So we could take any questions about that section if there are any.
I think we are at the same situation. People, let's give people a minute to write our questions.
And as a reminder, for if you ever have a question while I'm going through a section, feel free to just put it in the chat then. I think we'll continue on to the next section then.
All right, so no questions yet. I guess you can cover both questions from this portion on the next Q&A, right?
Okay, so correlation doesn't imply causation. But then the question is, then what does imply causation? We're interested in, we need to know when things cause other things. when is a treatment for COVID-27 actually effective against COVID-27? When is something to deal with headaches actually effective against headaches or preventing headaches? We need to know these questions. We need to know the answers to these questions. So that's what this section is about. What does imply causation? And I'll have to introduce a concept that you might have not seen before if you're not familiar with causal inference, which is the concept of potential outcomes. So it might take a bit of time to wrap your head around. I'll try to help with that. So say you're inferring the effect of some treatment or policy on some outcome. So let's just take this headache case that we were just looking at. So we want to know the outcome is headache or not headache. You have a headache or it goes away. So you want to know some treatment to get your headache to go away. And let's say that if you were to take a pill, then your headache would go away. You're happy in this picture. And if you didn't take that pill, then you would still have your headache. So if this were the case, so we're kind of talking about two hypotheticals here. What would happen if I were to take the pill? What would happen if I didn't take the pill? If this is the case that you would have a headache if you didn't take the pill, and then your headache would go away if you did take the pill, then we would say that there's a causal effect, that the pill is causing you, it is a causal effect on headaches. But if it were the case that when I don't take the pill, my headache would still go away, then we would say there's no causal effect, right? So whether or not I took the pill, my headache still went away. Okay, so there's kind of this key thing here is like, what is the outcome? What is the potential outcome that I would observe if I were to take the treatment or not take the treatment? So this is the intuition for potential outcomes. I'll introduce a bit of notation for it on this slide. So another way of denoting that you've taken the pill is this do t equals 1 or do 2 equals 0. That's the kind of stuff you would see in Yuta Pearl's notation. So your outcome, given that you do t equals 1, that you take the pill, this is a way you could denote a potential outcome. Where I here is basically talking about a specific individual. So specifically for me, that's what the I here denotes. Or a specific unit is another word you'll see. And then you'd have the same thing down here. It's just the do t equals 0 is changed. So it's like, what is your potential outcome evaluated at when you take the treatment or when you don't take the treatment? And this is commonly denoted, so this is potential outcome notation. One way of doing potential outcome notation is just yi with a 1 in parentheses, and then the bottom one, yi with 0 in parentheses. So that's the potential outcome under no treatment and the potential outcome if you were to take the treatment. So, given these definitions for potential outcome, then you can just write down the causal effect as just this difference between the two. So if it's the case that when I take the treatment, my headache goes away, so I get a 1 for my outcome. So 1 is headache goes away, 0 is I still have my headache. If it's the case that when I take the treatment, the headache goes away, and when I don't take the treatment, the pill, then my headache stays there, then I could plug those into this causal effect here, and I get that there is a causal effect. The causal effect is 1. It would have been 0 if the guy were happy here. So if yi0 were a 1, then the causal effect would be 0. There'd be no causal effect. Okay. So we've just introduced potential outcomes, the intuition and some notation for it. But there's this problem known as the fundamental problem of causal inference associated with this. So what that is that say I were to not take the pill. So I have a headache, but I decide I don't want to take the pill for whatever reason, then I would observe that I still have my headache. I would observe yi0 equals 0. but I would not be able to observe what would have happened had I not taken what would have happened had I taken the pill. Okay, so this top one, yi1, is counterfactual because it's counter to fact. The fact was that I didn't take the pill. What would have happened had I taken the pill is counter to fact. Okay, so since I don't observe yi1, then I can't calculate the causal effect because we're missing that yi1. And then similarly, if I were, say I did take the pill, then the other one would have been a counterfactual. So if I do take the pill, then yi1, I would observe equals 1, but I would not observe yi0. Say it is the case that yi0 equals 0, but I don't get to observe it because I chose to take the pill. So I still can't calculate the causal effect. So you might be thinking, well, I could just one day I'll take the pill, the next day I won't take the pill. And basically you'd be making some assumptions if you want to do causal inference in that case. But the main assumption is just that you're assuming that you're in the same state on the day that you take the pill and on the day that you don't take the pill, right? There's all these other factors, stuff going on in your body, stuff going on outside your body, and you're assuming that those are all kind of the same, controlled for, which is hard to do. Okay, so we have this fundamental problem, causal inference. How do we do causal inference when we have this fundamental problem? Well, so first, what I showed you just now, this difference is called the individual treatment effect. And you could just take the average of those. So it'll be clear why I'm doing this in a second, but say you took an expectation of this, then you get the average treatment effect. By linearity of expectation, you just have this, the average of the difference is the difference of the averages. And then the key thing is that these two quantities are not equal. So if we've observed some data on y and t, we can calculate, or we can estimate, these conditional expectations. But we can't necessarily estimate these expected values of these potential outcomes. So the reason that these two aren't equal is just correlation does not imply causation. So if you look at this graphic, some graphical intuition for that is that this top quantity is a purely causal quantity, right? We're looking at the potential outcomes. So it's blue here for this causal association. And then the bottom quantity is a combination of causal and confounding association. So I put blue and red here for that, it's measuring effectively the association flowing along both of these paths from T to Y, T to C to Y, and T to Y. Okay, so, key thing here, these two quantities are in general not equal, but there's a kind of a special thing that can make them equal. And that's randomized controlled trials. So, here's just copy and pasted from the last slide that these two quantities aren't equal. Well, with a randomized controlled trial, it actually eliminates the confounding association. So this confounding association is gone in a randomized controlled trial. Okay, what's going on there? Why is that the case? Well, one way of looking at it is that, I haven't said what a randomized controlled trial is. A randomized controlled trial is when you, say you're deciding to give the pill or give a placebo pill, like not give the pill. You flip a coin to decide for a given person whether they get the pill or not, if they're in the treatment group or the control group. So because it's a coin that you're flipping to decide the treatment, that means that the treatment is not determined by any confounders. So T can't have any causal parents because the only thing it's determined by is the coin. Like you could write that the coin is a causal parent. It's determining the treatment, but T isn't going to be determining anything else unless you choose to determine the outcome via a coin flip as well. I don't know how you would do that, but don't do that. You only determine the treatment from the coin flip, and so since that's the only thing affecting the treatment, then T can't have any causal parents. So there's no confounder here. C is not a confounder, it's just a cause of Y. Okay, so that's one way of looking at why randomized controlled trials are very special, why they eliminate confounding association. Another way of looking at it is that basically it makes the treatment group and the control group comparable. So in the shoe sleepers example, we had that the people who were waking up, or the people who were falling asleep with their shoes on, a lot of those people were going to bed drunk after having drank a lot of alcohol. Okay, so that's very different from the people who were going to sleep without their shoes on. Those people were going to bed without drinking alcohol. Well, if you were to, you could imagine going into people's rooms while they're just about to sleep, and you could like take their shoes off or put shoes on them randomly by a coin flip. That's how you would turn that into a randomized control trial. And then you'd make it so that you have roughly the same number of people who are going to sleep with shoes on after you've done your intervention. Roughly the same number of those people went to sleep after drinking a lot of alcohol, and then roughly the same number of people who don't have shoes on went to sleep after drinking a lot of alcohol. They're comparable groups. Okay, so what happens when you have this? So that's kind of two ways to think about how randomized control trials eliminate association, or eliminate confounding association. The first one is this graphical one. The second one is kind of just thinking about comparable groups. It's not really graphical. When you have this, then you have that these two quantities are equal. Okay, so in general, they're not equal, but when there's no confounding, like in randomized control trials, then they are equal. Okay, so that completes this then what does imply causation section. So any questions about this section?
We have one question. It might be more related to the previous one, but still going to read it. So sleeping with shoes can be an indicator of drinking the night before. If you want to know when you will have headaches, aren't sleeping with shoes and drinking kind of being the same for this prediction?
Yeah, so you're talking, basically it sounds like the question is like, how can I predict when I'll have when certain people will have headaches? And so association is kind of the same as predictive ability. So if two variables are strongly associated, then one of those variables is very predictive of the other and vice versa. So if you just care about prediction, which you might, then association is what you'd care about. Imagine though, in this setting though, that so you have one society where, so like two different populations, like a transfer learning type problem. So one society, it's not normal to sleep with shoes on, and then you have another society where it is normal to sleep with shoes on. Then what you learn about shoe sleeping's association with headaches in the society where it's not normal to sleep with shoes on, so you see that they're very associated, could be completely wrong in the society where it's already normal to sleep with shoes on. Then the two might be not associated at all. So yeah, so basically, like when you look at transfer learning, that association might disappear in a different population. but yeah, for causal inference, you want to just know the causal effect. So it's like, what would happen if I were to sleep with shoes on? Would it cause me to have a headache? It's basically when you want to decide what actions you'll take, which is like we're always deciding what actions we'll take. When you're in that setting, you want to know what the effects of those actions will be. You want to know what those actions will cause. You don't want to just know what they're associated with in the population, because it might not be that they actually cause those things. They're just associated, and you don't have the confounder that actually leads you to the outcome.
All right. No more questions at this point, so I think we can continue.
All right. So as a recap, we just saw that correlation does not imply causation, and then in the last section that how you could get causation. One example is with randomized control trials. Another setting is, what if you can't do a randomized control trial, right? So you can't go in and randomize the treatment. You can't go into people's rooms and flip a coin to decide whether you're going to put shoes on them or take their shoes off. So you just have data that you've observed. That's an observational study where you can't do an intervention. So, in the ideal case, you would have intervened on the treatment. You would have randomized the treatment so that you don't have any confounding, right? There's no confounding when you randomize the treatment. Everything will work out well. As correlation equals causation, or association equals causation in a randomized control trial. But in observational studies, you might have this confounding because you're not randomizing treatment, you're just observing some data. And why can't we always randomize treatment? Well, for example, there might be ethical reasons. So even if even if you have the willpower to randomize treatment, there's reasons why you can't do it. So say you want to measure the effect of smoking on lung cancer. For most people, you can't just randomize people to smoke or not smoke. I mean, maybe if you're like a dictator, you might be able to, but like ethically, you might not want to do that. There's also an infeasibility reason. So say you wanted to measure the effect of different like governance systems, or economic systems. So say communist, capitalist, you want to measure the effect of that on gross domestic product. Well, you can't just, it's like really hard to be able to randomize whole countries into an economic system. You can't just say, okay, well, you're going to be a communist country, you'll be a capitalist country. Unless you're a dictator of the world, I guess. And then there's cases where it's just impossible. Like there is no way you could do this. So say you wanted to measure the effect of of a specific gene at birth, right? So you're born with this genetic code, and then you go through life where you have these environmental factors influencing things as well, not just your genes. So say you want to measure the effect of a specific gene at birth on breast cancer. Well, after a person's already been born, you can't like go back and change their DNA. So in the future, you might imagine that maybe we can change people's DNA, but after they're already born, say you can't go back and change their DNA at birth because they were already born. So maybe you could change their DNA when they're alive, but their DNA at birth is the thing you care about because of these environmental factors, and you can't do that short of a time machine. So say you can't get a time machine, say like those are impossible, then it would be impossible to randomize that gene. So how do we measure causal effects in observational studies, given that we can't always do randomized control trials? And you might have heard the words adjust or control for confounder. So that's all you do. So you basically have to adjust or control for the right variables. So we'll call them W here. And if W is a sufficient adjustment set, I'll give you some examples of what that might be, and you can see it more about that in the course. But if W is a sufficient adjustment set, so it's the things you want to adjust for, then you have this. So you have this potential outcome where we've conditioned on the sufficient adjustment set. And then you could also write this with this do notation. There are two different notations for it. But these two quantities, the same quantity, are equal to this quantity that's purely statistical. It doesn't have any causal notion to it. So it doesn't have a do in it. It doesn't have a potential outcome in it. It's just the conditional expectation of y given t comma w. So if you have a sufficient adjustment set, you get this. So another way of saying this is like association equals causation if you've conditioned on this sufficient adjustment set. And so in this graph here, C would be a sufficient adjustment set. So if we condition on that, then you can think of it as blocking this confounding association. It blocks it when you condition on C there, which is the singleton variable in this singleton set W. Okay, so I'm not going to explain like why you can think of it that way. That's just kind of the graphical intuition, and you can also just do a proof with this kind of stuff without the graphs. But say you don't want to condition on W, then all you do is just the same thing. You get the same quantity, but then you just put an outer expectation over W. You just sum over W. So it's not, it's not too much more complicated if you don't want to. If you're not interested in quantities where you're conditioning on W, you just sum over W, the sufficient adjustment set. So let's see some more examples of sufficient adjustment sets. Basically, all they do is they block confounding association. So graphically, so we just saw this one, we could condition on C and that blocks the confounding association. And the shaded nodes, I'll show some sets that are more than one variable. So shaded nodes are examples of sufficient adjustment sets W. So in this graph, say we were to condition on C, but then also on another variable to block that other path that confounding association flows along. So here W2, and then it would be blocked at W2, or if we condition on W1, it would be blocked at W1. And you could throw in more variables like W3, it's still blocked at W1 graphically. This is how I think of it in my head. Okay, so these are good because then you've isolated the causal association. When you've blocked all the confounding association, then the total association will just be causal association. And just to like tell you, you have to be a bit careful about this stuff. There are examples where you have variables up here above these other variables, and you don't want to condition on them. So like when you have this kind of V structure, or an immorality is another name for it, because Z1 and Z3 have a child together, but they're not connected. In that case, you don't have to condition on Z2 because the association is already blocked by this kind of special causal structure, and you actually don't want to condition on Z2. It would open back up this path. It would make confounding association flow. So I'm not going to go into that, but there's just a little complexity there that you can see more about in the course. Okay, so to finish off, we will just look at this COVID-27 example again. So this table is the same table from that slide. And we're going to be looking at specifically the case where causal graph is this. So that was scenario 1. So what is the new thing we have? It's that we have this formula for how to make it so that association is causation, right? So we have this purely associative quantity here, and then we can get this causal quantity from that. That's the new thing we have in our arsenal. Okay, so what are the variables we need to control for? What's a sufficient adjustment set? It's just C. And the way we would calculate this is we just sum over C. So I've just taken this expectation over C. I just sum over it and multiply by the probability of C. That's just writing out that expectation for a discrete variable C, which in this case is discrete, right? It only took on the values of 0 and 1. Mild condition is 0 and 1 is severe condition. All right, so armed with this, we can now calculate this sort of causal quantity. So this is scenario 1. In scenario 2, the calculation would look different. You wouldn't control for C. So, now that we calculate these quasi-quantities, we see that, okay, treatment B is the better one, given that we're in scenario 1. And so all we've done is just plugged into this formula just to give the calculation for that, just to kind of illustrate what's going on. Say you first look at this mild column, okay? So you want to get the probability that you have mild condition. That's the first thing we'll multiply by. And that's just the number of people who have mild condition divided by the total number of people, okay? So if I add up these 4 denominators, 1,450, 500, 100, I get 2,050. And then if I calculate the number of people who have mild condition, it's just 1,400 times 50. So that's what's in the numerator there. Okay, so this is just probability of having mild condition. Same thing down here. And I'm just multiplying that by the mortality rate, which is mortality rate, that's this quantity, expected value of y given t comma c. So it's the mortality rate for that specific treatment and condition. So it's that cell in the table. Okay, I probably should have shown that earlier, but okay, so it's the same thing for the severe column, right? So you still have the same denominators, but now you have 600 in the numerator because 100 plus 500. And then same for these. Okay, so so looking at this formula, this sum it's these two terms because C is binary. That's why the sum is turned into just two terms, and that's how we calculated it. Okay, so the calculation for scenario 1 gives you the causal numbers that you would care about are these ones. And this is how we calculated them. The naive calculation, so that's how you calculate the total column, which we saw earlier. I'm just going to put it back there. We're not going to go through it, but it's the same calculation we went through earlier. The total column is just these numbers. And it turns out, actually, the total column is the one you would look at if you were in scenario 2. So, welcome to causal inference. That's the end of the talk. You can see these slides at the website if you want to see the slides. And yeah, thank you. So any questions about this last section?
Yeah, so we have quite a few questions. Let's start with the first one. Could you give an example of sufficient adjustment, aka W?
Can I show my slides again? I think they just, all right. So let me do a faster way. So basically, in this causal graph, C here is a sufficient adjustment set because it blocks this confounding association when you condition on C. In this graph, you have these confounding associations going along these two paths. One example of a sufficient adjustment set in this path is W2 and C, right? And you could have also taken out W2 and just put in W1. Okay, so these shaded nodes are the sets. And then in this graph, it's just an empty set in the graph on the right, say. So okay, maybe the question wasn't about the graphs. Say it was about like what these variables are. So in the COVID example, C is the condition. So mild or severe, and that's what C is in that example.
So moving to the next question. Theophilus is asking, you said that we could add the flip of a coin to the causal graph in case of randomized control trials. What keeps us from extending the graph by adding extra parent nodes with respect to the treatment in the same fashion without treatment controlled for?
Okay, so it sounds like you're talking about making other variables causes of treatment. And I might misunderstand the question, but you could do that. You could basically, if you're in control of the treatment, you can make treatment a function of whatever you want to make it a function of. And so whatever you make it a function of will be the new parents of T in that graph you do.
Right. Let's move to the next one. Dmitry is asking, what would you suggest as a resource to continue learning about causal inference, specifically for industry applications?
Yeah, so most books are written by academics, right? They're not written by industry people. So like if you want a solid understanding of the topic, you can read books. But if you're only interested in applications, I'm not super sure. There are probably applications books out there, but I'm not as familiar with them. I use causal inference in applications, but yeah, sorry, I don't know.
What about your book?
Yeah, well, so you could use my book in industry application. I'm guessing this person might have seen my book, and maybe, I don't know, if they haven't seen my book, I would recommend my book. Of course, I wrote it. It's at causalcourse.com, but there might be like, okay, there is a book that I talked to some. I'm forgetting his name. There is a book out there, a guy who was writing a book where he uses it. He uses it at. He's worked at multiple companies, and like I think he currently works at Barclays, the credit company, I think, and he's written a book, but I don't think it's out yet, and I don't know what it's called.
All right, it's not too easy to find, but I guess maybe if you remember the name or of the person or the book, could you post it on Slack?
Yeah, I can definitely do that.
Amazing. Yeah, moving to the next question. So what causality analysis technique or techniques would you recommend to start with for cross-sectional data? A bit of an explanation. Similarly, like Granger causality is the state of the art for time series data.
Well, so I don't think Granger causality is the state of the art for time series. So if you're talking about causal inference, like you're trying to infer causal effects, the book by Hernan and Robbins, at the end of their book, so these are two big guys in epidemiology, which they use causal inference there. Their book, at the end of it, the last part is all about causal inference and time series data. If you're interested in inferring the causal graph, right? So like what causes what, that's at the end of Elements of Causal Inference. So that's a book that's popular among machine learning people. So Jonas Peters is the first author on that book. At the end of their book, they do causal discovery in time series data. But yeah, Granger causality is I would not recommend that for causal discovery.
Okay. One more question, the last one. How do we decide on which variables are to be represented in the causal graph, given that we can conceive of continuum of events, or so it seems? For example, match catching on fire, sulfur on the match combining with oxygen. A bit of a tricky question, but maybe you got it.
So the events are continuous, or I didn't quite get it now.
Yeah, so let me try to read it again. I'm not sure I got it myself. How do we decide on which variables to be represented in the causal graph, given that we can conceive of a continuum of events? For example, match, as in, I guess, match to light a candle, catching on fire, sulfur on the match combining with oxygen.
Yeah. Okay. So, I don't know that much about chemistry, but like I imagine there's some chemical reaction taking place over time, where these different elements are, decreasing in quantity and such. So you can represent. You can just take time and then have a variable at every time step. So you have to quantize time to do that, but you have to choose how you quantize it. But so you have those different variables that you mentioned at every time step, and sometimes you'll see people collapse time, and then they're only going to have a small number of variables, where time is not relevant in it. But you can unroll that into different subscripts for the variables at different time steps.
Mm-hmm. Yep. So thanks for your answers. Some people might want to continue asking questions, and if you want to do that, let's do that on Slack. Brady, if you can join us on Slack as well, that would be very much appreciated. Now let's have an 8-minute break, and see you with the next talk in 8 minutes. Welcome back. I hope that you had a nice break. And I'm very happy to announce that the next speaker is Z Bank from Google Brain. She's going to give a talk called A Tutorial of Bayesian Optimization. And yeah, like, can't wait to hear your talk. The floor is yours.
Thank you. So, hi everyone. My name is Wang, and I'll talk about some topics around Bayesian optimization. So, if you have any questions, feel free to add in chat, or I'll read out your question while presenting. All right, so a little about what the problem is. Basically, for Bayesian optimization, we care about black box function optimization. So imagine, like, for example, you might have a robot and it's sort of complicated and has a lot of like different kinds of parameters, like the control parameter or how long the legs are, things like that. And in order to really make it work, you have to sort of try different kinds of these parameters and make it walk like as fast as possible or as stable as possible. So either way, you're going to have an objective, and we're going to call it function f. And the thing is, we are sort of viewing this as a black box because we don't know much about, like, within this black box how this parameter impact our robot. And eventually the goal is to try different hyperparameters sequentially so that we can get to a very good setting as soon as possible. And well, more formally, the goal is to find the argmax of function f by sequentially evaluating it. So this kind of problem actually appear in a lot of different scenarios. For example, in autonomous driving, we also have a lot of parameters to tune, which have a very big impact on how well it performs. In biology, for example, when people do something like gene design, it exactly follows this paradigm where it's really about how you design the experiment in order to find the gene that you want. And similar things happens in, well, molecular design, or and also, like, I'm not exactly sure what the audience's background is, but a lot of people really care about hyperparameter tuning and machine learning, because exactly like these various different kinds of problems, we also have a lot of hyperparameters like learning rate, momentum, well, the size of the network, etc., and they have a big impact on how well the model performs. So our goal here is to show that, okay, can we test well, hyperparameters in a sequence so that eventually we get a very low empirical loss, or like validation loss. And all these problems share some similar challenges. The function f is quite expensive to evaluate. Well, training machine learning models take a while. Doing wet lab experiments also take a long time. And sometimes these type of evaluations can take days. Well, second, f is actually a multi-peak function, which means that it doesn't only have one peak. It might have like several different peaks, which makes the global optimization problem more difficult. Third problem is that, well, we don't really have gradient information. Suppose we're trying to access the validation error of a network. Well, we don't really try, well, in these cases, we don't really have exactly what the gradient is. And similarly, this problem goes to like robotics and these biology type of problems. And so fourth is that the evaluations can be quite noisy. And as you can see in robotics problems or even like machine learning problems, depending on what exactly your machine status is or like the random seed, you might have a slightly different evaluations. All right, so from all these, well, I must say that for gradient information, in some situations, Bayesian optimization can actually make use of gradients, but this is not really within the scope of this talk. All right, so so thinking about like how to solve this problem, one really simple approach could be that we use grade search. And that is indeed the type of solution that a lot of people adopted when we are facing hyperparameter tuning method problems in machine learning. And we're basically, well, trying to take a grade and then evaluating them one by one. The other approach is saying, well, we can do random search. It has been shown that random search could be better than grid search, but we are still missing a lot of good points because we're not really utilizing any information of what has been evaluated before. So, right, exactly. The problem is that a lot of evaluations are actually wasted in this case. And here's actually where Bayesian optimization comes in. It's really a method that tries to be smarter about how to choose the points to evaluate. And here the key idea is we're trying to build a probabilistic model of the function f. And then we're going to use this probabilistic model to decide where to query decide where, how to choose the query points that we're going to evaluate. And once we choose these query points, we're going to update the model and then do the same loop. So there are a couple of questions in this particular idea. So one is what we do with the probabilistic model. And here, well, notice that we're actually doing a probabilistic model for functions, which means we're trying to derive a distribution over functions. And the second problem is how do we choose the query points? And typically in Bayesian optimization, the way we do it is by using a decision criterion, which we call the acquisition function. And it really makes sense because it's the way we acquire information. It's the way we try to acquire more data. And that's why it's called the acquisition function. So in the end, the idea here is that we are trying to transform our global optimization problem of an expensive and difficult to evaluate function f into a series of optimization problems for this much easier to evaluate function, this acquisition function. So the hope is that once we loop through this T iterations of optimizing acquisition functions, we can find a pretty good point that give us very good value for the function f. All right, so I want to talk about these two questions before we dive into more complicated issues. And the first one is the probabilistic model. So in case like people don't know Gaussian process, I'm going to like do a brief introduction on what it is. So Gaussian processes are usually the kind of probabilistic model we use for Bayesian optimization. And it basically describes a probability distribution of the functions. And you can think of it as sort of as an analogy from the Gaussian distribution to describe numbers. And then, well, the Gaussian process is actually a very basic distribution to describe functions. So the only assumption we're using here for Gaussian process is that any finite set of function values is a multivariate Gaussian. So what that means is we have, so all these colored lines are actually samples from the same Gaussian process. And if we just look at one particular line and we look at the function values at different locations, x1 through x3, all these three function values actually follow a multivariate Gaussian distribution. All right, so to be more precise, what we're saying here is that a Gaussian process is defined by a kernel function, k, which takes in two values, two inputs, and then a min function, mu, which takes in one input. And once we have a finite set of inputs, x1 through xn, they follow a multivariate Gaussian distribution where the min is parameterized by, well, the evaluations of min function mu at all these inputs. And then the covariance is described by the kernel functions evaluated at every pair of inputs. And once we have a function sampled from this Gaussian process, we can observe noisy output at any input x tau. So y tau is additive, it can have like additive noise, which is the sum of the f of x tau plus some noise, and this noise is sampled from a normal distribution. All right. So the nice thing about using a Gaussian process here is that we can actually get closed form posterior inference for our GP. So here's an illustration of what it looks like. Here, left has samples from the posterior, from the prior, and then for the prior, you can see well all these colored lines are samples of the functions, and then we have zero mean and some, well, sort of like uniform standard deviation. But once we observe some points like the dotted points, we are constraining our functions to have those values at those dotted points, and hence we're getting very different variance predictions and mean predictions, and all of these are in closed form. Okay, so going to talk about the other part of the question, which is the acquisition function. But in case anyone have questions, here is probably a good place to pose. I'll probably pose around a few seconds. No questions? All right. So let me dive a little more into the acquisition function part, which is actually a very critical part of space optimization, because this is where we make the selection, where we make our, try to derive our strategy. Okay, so, all right, we already know we're going to use a Gaussian process, and now here's how we're trying to do acquisition functions. Okay, so the first example I would like to give is GPECB. It stands for Gaussian process upper confidence bound. And to me, I think it's a very interesting approach that makes a lot of sense. So here's how it works. We're assuming that, we have a prior, which is the Gaussian process. And then at each iteration, we're going to predict the posterior. And once we get the posterior, we're going to pick an input by optimizing the upper confidence bound. And the upper confidence bound is defined by the combination of the mean function and the standard deviation prediction. So both of them are posterior. And so just to show an example of how this works, we have, so here we have a function which is in red, and the mean function is in blue. And our posterior, well, our standard deviation prediction is in gray. So in the first iteration, everything's sort of similar. So it's going to pick a random point. And once it sees, oh, this is how well this particular point does, it's going to look at the upper confidence bound. And in this case, it actually ends up at this particular green point. So it's going to think that, okay, if I'm being very optimistic, then this point is really going to give me a very good value. So it's going to query this point, and it sees that, oh, it actually didn't achieve the desired value I wanted. But it still gives me some information about how this function works. So it's going to look at the upper confidence bound again, and still being very optimistic, and tries to evaluate more points. It's going to repeatedly do this particular process, and as you can see, the upper confidence bound actually, well, the max of the upper confidence bound actually shifts quite a bit. And as we continue to do this, we may end up evaluating the boundary, but eventually we look at the place where it actually achieved the global optimal. Once it achieved the global optimal, the interesting thing here is that because the parameter that we use here, which is 3, which is trading off between the standard deviation and the mean, actually thinks, oh, somewhere else might also have a much higher value. So it's going to evaluate, and then realizing that, oh, actually it's not as good as the one we've seen before. And this is when it starts to realize, oh, this point is really good, so let me stay around here. It might not keep staying around here, because once we reduce this the uncertainty around this point, it's going to think, oh, somewhere else might have bigger value. But okay, eventually, all right, we're at this point, and eventually we're going to end up at our global maximum. All right, so here is roughly how GPU-UCD works. You can see very simple, very straightforward. The idea is very simple to understand. So some other examples. So this particular one is called probability of improvement. And we're sort of asking the question, once we have the observations, maybe we can evaluate the improvement, the probability of improvement. It's like exactly what the name means. We're going to evaluate the probability of improvement, and as the acquisition function of our base-opt approach. So in this case, what we're doing is we're looking at the probability that f of x is improving upon the best observation, which is the max of y tau. So tau is from 1 to t. As an illustration, if you look at this particular plot, basically what we're seeing is that recall that our function f of x, if we just look at one single point, it's a Gaussian distribution. If we look at multiple points, it's a multivariate Gaussian distribution. So here we just look at one particular point, f of x, and we're going to, cut our distribution at max of y tau. And then we take a look at all the probability that if the function f of x is improving upon this max value. And then we're using that as our as our acquisition function. And this also makes a lot of sense, right? except that it sometimes doesn't work super well in practice. So what people do is to add a small epsilon to this max of y tau to give it more power to sort of explore. Okay, so another very similar acquisition function that a lot of times behaves rather differently is expected improvement. And oops, sorry for the animation, but all right, so here we're doing something quite similar to probability of improvement, except that here we're looking at the expected improvement, which is integrating our function f over the improved area. So because everything's still Gaussian, we can still actually get a closed form evaluation of this particular expected improvement. So, and then in practice, in fact, a lot of times expected improvement shows up as more robust than probability of improvement. All right, so these are some what people might call heuristics, because they're like strategies that people come up with, which sort of make sense intuitively. But one strategy that really stands out to be more sort of principle, well, depending on how you define it, is entropy search. So entropy search actually have a lot of methods that extended from this particular method. So for entropy search, what we're looking at is the mutual information between the point we're going to query and the location of the global optimal. And of course, given our observed data. So here are two particularly interesting extensions. One is the original entropy search. So this is because we use one particular form to write out our information gain. So H here is the entropy. So it can be written as either the difference between the entropy of A and entropy of A given B, or the entropy of B and entropy of B given A. So for entropy search, we're doing, well, the entropy of the point, the location of the global optimal, and the location of the global optimal given our data, given our new point to query. And for another method is called predictive entropy search. So in predictive entropy search, what we're doing is that we're trying to look at the other form of the mutual information, which is the entropy of our point to query and the difference between the entropy of point to query and the entropy of the point to query given the location of the global optimal. So these both makes a lot of sense, because eventually what we're doing is that we're trying to collect information in order to find the global optimal. So we already have the tools in information theory or probabilistic theory, which says that, well, let's look at the mutual information, and we're going to simply do that. So the only approximation they use here is that they're looking at one point at a time. But if we're trying to be really accurate, then we will look at a set of points at a time. But then, of course, as you can see, well, if you use a set of points, the information gain is going to be very difficult to compute. And even for this one single point, we still need a very heavy approximation in order to get the values we want. So another method that I would also like to talk about, which is also an extension of these ideas, is to sort of look at the location of the optimal. We look at the global max value of this entire function. So here, what we're doing is that we are moving from the d-dimensional input space which give us actually quite a lot of trouble to approximate what this information gain is. And we're moving from that to the one-dimensional output space. So in this case, well, both values, the y and y star, are actually both one-dimensional, and it makes it a lot easier to compute what the information gain is. And the sort of thinking behind this is that, well, although we care a lot about the location of the global optimal, if we get the information about the max value, potentially we're still getting a lot of information about the location as well. Okay, so for this particular acquisition function, again, we can write out the information gain. And then what we see is that the first item is simply the entropy for a Gaussian. So because y is a Gaussian distribution. And then the second item is, well, it can be approximated by the entropy for truncated Gaussian, because we know that our our function value y must be smaller than or equal to the global max value. So both of the terms have a closed way of computing it, and you can eventually write it out in closed form. All right, so just to give you a brief sense of how it works, if we try to, okay, so actually I forgot to show this. So here, eventually, we're going to compute this closed form acquisition function by summing over the samples of max values from a set. And the main question here is how we can sample it. So here's a very simple idea of how we can do that. We know that at each point, we're going to have a Gaussian distribution. So, although this theorem doesn't exactly apply, but we also know that the maximum of a set of IID Gaussian variables is asymptotically described by a Gumbel distribution. So although it's not IID, and we can still try to sort of assume, well, assume if they're IID, we can actually approximate the max value of the representative points by a Gumbel distribution. And then sampling from that Gumbel distribution is very simple. Okay, so this is one idea. And in fact, it's also performing quite well than the predictive entropy search method. So both the predictive entropy search method and this max value entropy search method uses samples. So we're looking at samples from 1, 10, and 100. So for PES, it's sampling the location of the optimal, and then for MES, it's sampling the max value. And what we can see is that as we increase the number of samples for PES, the performance is increasing, but for MES, it sort of didn't really matter. And then one more good thing about this approach is that we can have very low runtime. So computationally, it's very cheap comparing to other entropy search methods. All right, so and one more important reason that I'm talking about all these acquisition functions is that there are actually some very interesting connections beyond them. So for the MES approach, if we just look at one single example, one single sample of our max value, we can actually see that it's a function of this gamma y star of x. And if we plot out the relationship between alpha t, which is our acquisition function, and gamma y star, we are, they're actually monotonically decreasing, which means that optimizing the acquisition function is equivalent to minimizing our, this particular function gamma y star of x. And what that And so interestingly, this actually also leads to some connections to existing methods like probability of improvement and upper confidence bound. So in fact, for probability of improvement, it is also minimizing this gamma function by switching this y star to the max of y tau plus some epsilon. And then for the GPU-CB approach, this is actually also minimizing our gamma function, except that it's using this parameter, which is the max, which is actually the maximum upper confidence bound. So they're all equivalent to minimizing this y theta of x if under different circumstances of what theta is. So this actually also carries over to the upper confidence bound approach. We can show that by switching what this beta parameter is, both MES and PES are doing exactly the same as optimizing an upper confidence bound, except that they're doing this under different special cases of what beta is. Oops. So, so if you are going to look at beta optimization research, one thing you're going to see a lot is the regret bound. And what this regret bound means is that we're trying to characterize how well we're doing in beta optimization by looking at the regrets. Here, so there are several different ways of defining the regret, but here I'm using the difference between the maximum value of the function and the maximum value that exists in our observation. Okay, so so here is roughly an overview of what these two different papers are saying. So for if we assume that our function f is a sample from the GP, then our GPU-CB approach will obtain this particular regret bound. So notice that here we're using the Gaussian kernels. It's okay if you don't know what it means, but other kernels might be a little different. So I think the interesting thing to see here is that so D is the dimension of the input, and as we increase the dimension of the input, we're actually going to get a worse regret bound. And for MES, it's doing something pretty similar. It also have an exponential dependency on the dimension, but then the other terms are a little different. So anyways, these are sort of like the typical regret bounds that you may see in different papers. And actually, a lot of times, the regret bounds are derived in a similar way to the GPU-CB method in Srinivas et al. All right, just to summarize how this up works. So we have posterior estimation, and then we're going to define acquisition functions. There are a lot of them if you look at the literature. And then we're going to evaluate this function f at our points that achieves the best acquisition function value, and then we're going to repeat. So this is basically the process that you need to know in order to understand these kind of methods. Okay, so for, I don't know how much time I have left, but I don't think we're going to cover all of these topics. So for some of these topics, I have the slides for some others, I'm like the auto constraints, I don't have the slides, but I can still talk a little bit about it. I believe the organizers are going to bring up some questions.
Yeah, we are going to do that right away. We are going to launch Slido. where you can select which talk you want to, which topic you want Z to cover now. All right, so please vote for the topic which is most interesting for you. So it seems that we are approaching the winner, and I think we can close the poll right now.
All right, let's talk about robotics. It's interesting to see that people are very interested in robotics. All right, let's go. So I must say that my PhD was actually in machine learning and robotics, and it has a pretty big emphasis on robotics applications. So actually, we don't call it robotics applications because what we're really doing is that we're trying to solve robotics problems, and then it turns out Bayesian optimization is a very nice tool to deal with some of the problems. And that's how I sort of started doing more research in this area. All right, for robotics, we definitely need some videos. So here, it's actually part of my PhD thesis. The robot, which is a PR2, is trying to deal with a long horizon task. I forgot what it is. Oh, it's trying to cook a broccoli, and that green little thing, the box, is what we used to call broccoli. And then it's going to cook it and then serve it on the plate, and then returning home. So here, the second task is that it's trying to make a cup of coffee. It's going to pour the coffee, to scoop some sugar. Of course, they're not really sugar. And then it's going to stir it, and that's done. So, right, so, well, we can keep it plain. So the reason I'm showing these two simple examples is that I just want to tell you that a lot of robotics tests that we really care about are actually very complex, very long horizon. It can be stochastic because the robot arm, when it's executing, it's not doing exactly the same action or same control as it used to. So it might place, like for the same placing action, it might place the object slightly different than where it placed it before. And in these particular tasks, we're also assume everything's fully observable. So that is to say, the robot knows exactly where things are, including the balls, the cups, the green blocks, and it's where it is. So the reason that we're making that assumption is is exactly to make our lives easier, because doing partially observable actions, doing partially observable states is a lot harder than the fully observable one. And if we can't do all these complex tasks in fully observable cases, there's little hope that we can deal with the partially observable case. All right, so there are a couple of questions in how to accomplish these tasks. The first one is that we need to enable the robot to have skills, which means it needs to know how to push, how to pour, how to grasp, how to place. And for each of the skill, we need to have a way of enabling it to learn how to do things. In our case, we want to do this so that the robot can start from anywhere, and then it can go to a goal position that's specified by us. So one problem here is that a lot of these skills are multimodal, which means that we repeat the same one, but it ends up at different places. Excuse me. All right, so here's how we're doing this, very roughly on a high level. Suppose we have a starting location S and a goal location G. The thing we're trying to do is that we're trying to select what the action is in order to go from start to goal. And that might involve several smaller actions. So here the action means, well, we're taking one little step, you know, and we can't really take that little step from start to goal. So the one very simple way of doing this is to think of it using like a reinforcement learning framework. I mean, by reinforcement learning, I really mean dynamic programming. So if you don't know this this function, that's okay. But if you know it, it's basically the like the Bellman updates. And then we're going to select our action by optimizing this particular function. But in our case, this particular function involves the transition from previous state to the current to the next state. And this particular transition will be computed based upon our collected data. And this will be computed only on demand, which means evaluating this function actually becomes quite expensive. But then, yeah, coincidentally, we just talked about optimizing expensive functions, right? And what we can do here is that we can solve this by Bayesian optimization. All right, so here's a little animation on how this works. Don't blink. So we're going to we're going to select the actions by optimizing this function repeatedly at different states. And then once we reach the goal state, we're going to use the real-time dynamic programming approach and then backtrack to update the values for each state. So for this real-time dynamic programming approach, we're actually doing this repeatedly. So it's optimizing this function repeatedly, and then every time it will actually go to a different. It might use a slightly different action because our actions are stochastic. All right, and then eventually, once we repeat this enough, we're going to be able to update the values for the states that it's going to encounter if it's trying to travel from start to goal. And then once we deploy it, it will know at each particular state where to go. Oops. All right. So here's so that's pretty much like how we are trying to learn the skills, but there could also be like other approaches, which I'm not going to cover. But then another big question is, how do we plan with the learned skills? So what we talked about is just a one single skill, but it's eventually, once we try to do the long horizon task, it's a very complicated, well, it involves very complicated combinations of actions or actually of skills. All right. So here's what happens. Like a robot might be trying to like make a cup of coffee, for example, and then it sees that on the table there are several different tools it can use, and it's going to start thinking, okay, from my current state, if I do this and that, pick up, push, or pull, where do I get? And it's going to think in like a tree-styled search approach. And then eventually, if it hits the goal, it will take that particular route. So a question here is, our skills here actually involve continuous parameters. And in order to do tree search, we need to sample them. And then another question is, how can we do tree search on both the discrete and continuous variables? So the second part is actually handled by an approach that I didn't cite here, but it's from my lab mate, Ken and Garrett. And it's basically doing something like that. And our key question here is really how to sample the scale parameters for our planner. So this is assuming that we already have a planner that can deal with that, which actually we do already have. So here we go from the pouring scale, and then there are some continuous parameters, x. So again, it's very similar to the Bayesian optimization setting. We are trying to evaluate how good these continuous parameters are in order to decide which one to train next. So yeah, that's all. That's like another example of how we're using BaseOpt in our robotics problems. All right, cool. Okay, so actually that's my last slide for the robotics part. I'm not sure if we have more time for other topics, but I'll try to. Okay, 2 minutes. So, all right, so I just want to tell you a bit more about what's going on, like sort of at Google. And we actually recently had a Google BaseOpt speaker series, and we are releasing all the videos, and 4 of them are actually already online. So you can search Google Tech Talks on YouTube to learn more about what's going on in this field. We actually have, well, a talk from Andres Krause and also Yasha Bengio. They're all talking about really, really interesting topics. And if you like this talk of tutorial, I'm sure you can understand all of them. All right. So yeah, let's see if we have any questions.
Yeah, we have a few questions, so we can go to the Q&A part right now. And let's start with a question from Dmitry. He asks, Gaussian processes are often expensive to evaluate when there is a lot of data. Can we use alternative methods, e.g. ensembles? And if yes, what do people prefer to use in practice?
Yeah, that's a very good point, and that's actually something a lot of people are thinking about. So can we use ensembles or even like Bayesian ensembles, Bayesian neural nets, in order to make this process easier? So, so my take on that is, I mean, you certainly can, but then the problem is, for the ensembles, once you get a new point, you have to update it. But training ensembles is very difficult. I mean, it takes a while. In my understanding, it takes quite a while. So in order to use ensembles to to just update one point is not very economical. And so what people typically do is that if we are in the batch large scale setting, then it might make more sense to do ensemble approaches. So I actually do have a slide on that. Oh, all right. Let me try to find it. Window. Okay, cool. So on the left, there's a Mondrian process, which is actually also an ensemble approach, but we're only using it for the a batch of queries instead of one query, because I mean, in this case, so for Mondrian process, it's actually not super expensive to update one example. but still it works. It sort of like work very naturally for batch queries, because for each ensemble, you can, well, for each member in the ensemble, you can sort of predict one query to evaluate, and then if you aggregate from all the ensembles, or all the members in the ensemble, then you can get a batch of queries, and it works very naturally with that. Yeah, that's it.
All right, I think we can move to the next question. So Robin is asking, so how do you choose the prior?
Oh, interesting. Yeah, I also have a slide on that. Actually, a topic on that. There are a lot of, I mean, there are, can we, okay, let me try to share it again. Can you see this here? Okay, thanks. All right, so this is a whole different topic. I mean, they're super related, but there are a lot of questions on where do we get the prior, and if we don't have a prior, how do we get the regret bound? And if you really look at this type of problem, it's sort of like a chicken egg problem, because we're in practice, we're estimating the prior from the data, and then we're collecting the data based on our prior. And I mean, I think it creates a lot of issues. And in fact, I think a lot of people actually do also think like that. And there are some methods to try to alleviate this issue. And this is actually something I'm still working on. One particular potential solution could be that we try to do this by learning this prior from the similar functions. So similar to estimating a Gaussian distribution, we can estimate a Gaussian process if we have enough examples. And in this case, examples mean function examples. So if we try to do that, I mean, all right, there are a lot of different names for this. If we try to do that, I'm going to skip those. But eventually we can actually we can also reach a regret bound, which doesn't require the fact that we know the prior. We're going to, there's no assumption on this prior, or this Gaussian process is known ahead of time. Yeah, so that's like my method of doing this. But I think a lot of people have other approaches. Like, for example, I believe there were papers where you can adapt the length scales of length scale based kernels, and then you sort of like decrease the length scale bit by bit so that you're still encouraging exploration. Yeah.
All right. Can we move to the next question? Yeah, so Auxis is saying, fun fact, did you know that Professor Jonas Moskus, who coined the term Bayesian optimization and introduced expected improvement acquisition function in 1978, worked in Vilnius, Lithuania?
Sorry, worth what?
So Auxis is just sharing this fun fact that the professor who invented the term Bayesian optimization and introduced expected improvement acquisition function actually worked in Vilnius, Lithuania. There we are doing this machine learning workshop today.
Oh, interesting.
Yeah, just a fact for trivia.
Yeah, I guess people there can talk to him.
Let's move to the next one. Why we care about the regret bound? Is it related to the online learning?
Regret bound, right? So, why do we care about the regret bound? I mean, that's actually a good question, because a lot of people don't care about the regret bound. And so, I mean, I think like to me, so when I was in my PhD, actually none of my advisors cared about the regret bound, but we still had it because because they sort of didn't really care because they're roboticists, and they always thought of me as a theoretician once I showed them, oh, here are the regret bounds. But I think the real reason is that I believe we need some kind of certifications for machine learning methods. This certification can come as a regret bound. It can come as well, something that sort of like guarantees, oh, how well I can do once I achieve a certain, once I reach like say a certain level of data collection. And I think it's super necessary for a lot of scenarios. So personally, I worked a little bit on autonomous driving before as an intern, and I realized like it's really important that we have certifications for our methods. And this is something like machine learning really lacks. Like we can definitely get a lot of theoretical guarantees, but all these guarantees require some kind of assumptions, and they don't really match real-world scenarios. So I'm not saying that this is like if they don't match, then we don't do it. I think these are just like gradual steps that we try to take in order to finally reach a step where we can say, oh, if I do like say X-rays of patients, then I'm guaranteed to be like 99% accurate, or I can provide some kind of interpretation about why I'm making a mistake. So all these sort of things, I think, sort of comes to this question of what kind of certifications can we make for machine learning methods. But yeah, we're just taking like baby steps right now.
All right. I think that's all the time that we had for questions today. So thank you very much, Z. And I hope that you had a good time. I hope that everybody, all the participants had an interesting time listening to your talk. I think that we can move to the outro right now.
Okay, thank you. Thank you, everyone.
Thank you. All right, so let me do a quick closing statement. I hope that you had an amazing day today, and I'd like to thank all of today's speakers, and I also would like to thank all of you who are participating in Vilnius Machine Learning Workshop today. Tomorrow we'll have at least equally interesting day. We'll have 4 outstanding speakers. First of all, we'll have Andrew Jessen, who is going to talk about identifying causal effect inference failure with uncertainty-aware models. We'll also have Virginia Agleti, who is going to talk about causal Bayesian optimization. Then we'll have Audrūnas Gruslys, who is going to do a talk about introduction to reinforcement learning. And finally, we'll have Karolina Džiugaitė, who is going to talk about the progress towards understanding generalization in deep learning. At the end of the day, we're going to have a Q&A session, a panel discussion with Razvan and Viorica, like organizers of today's workshop. And even more, I guess, interesting that we are going to announce the winners of the book awards and 3 awards tomorrow during the welcome ceremony. So don't miss the welcome ceremony at 10:15 UK time or 12:15 Lithuanian time. Because you learn who actually won today quizzes, and we are going to announce the winners and announce the books which we won. We'll also announce the 3 awards. That means that all the participants of Vilnius Machine Learning workshops will get a tree planted for them. And thanks to your participation, you are going to help the environment. And actually, because of you, there is going to be a tree planted somewhere in the world. We'll also have a special message from the Artificial Intelligence Association of Lithuania about our future plans and our planned future events. So very, very interesting. And I hope you're going to be excited about that. Lastly, during the last break, so just before the panel discussion with Ruslan and Viorica, they're going to announce the Eastern European Machine Learning Summer School Project Awards. So they're going to announce the winners tomorrow during the last break. So don't miss it because it's like super important. So that's all the messages that I have for you. I had an amazing day today. I can't wait for tomorrow. Let's keep the discussion going on Twitter, on Slack, and see you tomorrow. Bye-bye.